So let me reshare my screen. Sorry for the delay, guys. Again, welcome to this session. And I know we were supposed to meet over here in the island of Rhodes in Greece, but due to the pandemic, we're not able to go there. But I'm just still want to try to share this picture with all of you guys, just to pretend we're over there right now. And this kind of scenery reminds me of the good time that we had 2 years ago in Hawaii, in Maui, when we had ITSC2020. Good memories. But hopefully we'll have a fruitful sessions today as well. If I go to the next slide, you can see we have covered a lot of topics. I will go through those slides, introduction slides, very quickly, maybe in 4 or 5 minutes. We cover Sumo, Vism, MSOM, Unity, which just went IPO on Friday, LGSVO, Carta, Human in the Loop, Hardware in the Loop, and more. And the presenters are from variety of organizations, not just from academia, like those top academia research organizations like Omtree, TTI, Berkeley, UCR, and McMaster universities, but also have presenters from industry and national labs like Toyota, LG, and Argonne National Lab, Oak Ridge National Lab, which I would say all those presentations are very interesting, very exciting. I list the schedule on the right side on every page. You can check. So the goal of this workshop, again, is to identify emerging simulation tools and technologies that are used to test and evaluate connected and automated vehicle technology. So not just connected and automated. It can be connected vehicle only, it can be automated vehicle only, it can be both. And you will see that in most of the presentations. And again, another round of welcome to all of the attendees from our workshop organizers. And I want to thank Jiaqi, Guodong, Guoyuan, Yiheng, Hao, and Chris. Thank you all for organizing this workshop with me together and invite all those attendees. Really appreciate it. We have so many attendees right now, and I attended some of the other workshops yesterday, not as many as we are. So hopefully we'll get more, and the presenters, they will present very, very exciting work. Special thank to Jiaqi, who hosted or who initiated this idea, but he was so busy at that time moving to UCLA, so I take over and host this workshop for all of you. And I think workshop speakers, thank you all again to accept our invitations, and really looking forward to all your talks later. We will introduce the speakers before their presentation, so I won't elaborate too much on here. So one last slide. This is our tentative schedule. And we have 10 speakers, 10 very exciting presentations. And I think we might go a little bit over time because some of them, they will spend maybe 20, 25 minutes. And you can see I split each hour slot by either 2 or 3 presentations. So maybe go a little bit over time, but it's fine because I just checked with the host of ITSC. We can go over time, but we will still try to catch up. And there will be a break after Guodong's presentation here, maybe 10 or 15 minutes. So Chris can lead a social session, discussion session, or maybe just have a casual chat with everyone regarding the presentations or any other topics we want to discuss. If that went well, we can have an extended discussion session after the last presentation. So without elaborating too much on this, let me start the first presentations. Let me share the screen once again. Share another screen. So put this video up here. Reshare screen. Okay. So the first presentation came from Dr. Shuo Feng. He is going to, so actually he's online right now, as you can see from the video, but he preferred to present this video through this pre-recorded video. present his work by this pre-recorded video. And again, to all the attendees, if you have any questions, just feel free to type that into the chat box, so I can pick out some of them if they are good questions to the presenters. And the presenters can also answer all of your questions in the chat box in real time. So Dr. Shuofeng is currently a research fellow at University of Michigan, and he received a bachelor's and PhD degrees from the Department of Automation at Tsinghua Universities. He was also a visiting PhD student in civil and environmental engineering with the University of Michigan from 2017 to 2019. His current research interests include testing, evaluation, and optimization of connected and automated vehicles. So I'll go ahead, play this video, and let me check whether the audio sound is available. Let me reshare one more time to make sure. Share computer sound. Okay.
Hello, everyone. I am Shuofeng, a postdoctoral research fellow from the University of Michigan. It's my great honor to have the opportunity to present our recent work at this workshop. The topic of my presentation today is Safety Assessment Simulation Platform of Autonomous Vehicles based on Sumo and Kala. First, why is AV safety assessment important? Because the AV is not safe yet. Here are two well-known fatal crashes regarding autonomous functions. Although the development of autonomous vehicles had attracted significant attention, the safety issue had hindered the progress of its wide-scale deployment. There exist major three testing platforms, including simulation, test facility, and on-road test. Comparing with the test facility and the road test, simulation has its unique advantages because of its controllability, repeatability, scalability, and efficiency. Therefore, most testing miles are conducted by simulation. For example, Waymo has driven more than 10 billion miles on simulation, which is much longer than its on-road test. Simulation plays a very important role for the AV testing and evaluation. Here are some examples of AV driving simulation platforms used by AV developers such as Waymo, Audi, and NVIDIA. The bottom shows some simulation platforms commonly used by research community, including Montemeto, Prescan, and Kala. The Kala is open source, so to make the platform open source, we will use Kala in this work. One key problem of these platforms is the lack of the fidelity of traffic environment. This is a basic framework of closed-loop simulation, where the AV mainly includes perception, decision, and control components. For the simulation platform, first, it should resemble the vehicle dynamics of AVs so that the behaviors of the AV can be well simulated. Then, the AV should be evaluated interacting with the traffic environment. So the traffic model are required for generating the environment. The right figure shows an example of the simulation environment. We can see that the traffic has significant influence on the performance of the AV and the test. Last, the simulation should provide real-like perception inputs to the AV sensors. In all these components, the fidelity of the traffic environment becomes a bottleneck for the simulation-based safety assessment of AVs. Here are some existing methods for generating the traffic environment. The simplest way is to design test metrics based on expert knowledge. However, it suffers from subjective biases and limited scalability. Another method is directly using the logged driving scenarios from data collection vehicles on public roads. However, the logged scenarios are fixed, so the traffic vehicles cannot interact with the AV and the task. One promising method is to borrow traffic simulation tools from the transportation domain. Here are two well-known traffic simulations, Vissim and Sumo. They were designed for transportation purposes, such as traffic congestion and emissions, and good at large-scale networks, multimodal road users such as cars, buses, trains, bicycles, pedestrians, and traffic management such as traffic assignment, speed limits, traffic lights. Therefore, a basic framework of simulation platform can be constructed by integrating these two types of platforms. The traffic simulation, such as VSIM and SUMO, can provide a scalable network, multimodal traffic, traffic demand, traffic management. And the autonomous driving simulation can provide high fidelity vehicle dynamics, diverse sensor models, high definition maps, and road integration. The road integration also provide convenient way to involve high fidelity AV models, which can be developed based on AutoWare or Baidu Apollo. With the framework, the remaining problem is that most existing traffic behavior models of the simulations lack the fidelity and cannot be directly used for the AV safety assessment. The major goal of existing behavior models is to evaluate the traffic efficiency and emissions of the large-scale transportation systems. Therefore, these models were designed to roughly capture the normal behavior patterns, and usually only a small set of human driving data is used for the model calibration. For the AV safety assessment, however, one major goal is to evaluate the accident rate of the AV when driving in the real-world traffic environment. As shown by naturalistic driving data, for human drivers, the accident rate is about from 10 to the power of -6 to 10 to the power of -8 per driving mile. This rarity requires that the traffic behavior models should be precise in both normal and real conditions for the safety assessment. Comparing with existing models and AV safety assessment requirements, there is a huge gap that needs to be filled. We denote this problem as the naturalistic driving environment modeling problem. The goal is to model and generate the NDE, which should be stochastic, naturalistic, and accident inclusive. Essentially, the traffic models should be distributionally consistent with real-world traffic environment. Here is an illustration of the key idea. Here, the x-axis denotes the behavior action given a state, and the y-axis denotes the probability of the action. If this distribution is the ground truth in the real-world traffic environment, the NDE modeling should capture not only the normal conditions, but also the real conditions. Let us further explain this basic idea. Denote state and action of vehicles as S and A, and the vehicle behavior model as the function F, mapping from S to A. The goal of NDE modeling is to construct the function F, which should be a stochastic function, and its distribution should be consistent with the real-world traffic environment. To achieve this goal, we propose a framework of the data-driven NDE modeling, including 3 steps. The first step is to collect large-scale naturalistic driving data and pre-propose the data. In this work, we utilize the data from Armtree at the University of Michigan. The second step is to model the vehicle behaviors based on the data. The most straightforward way is to use the empirical distributions from the data, but it could suffer from the data noise, so we designed an optimization-based smoothing method to keep the empirical measurement distribution consistent. After that, the last step is to generate the entire data-driven NDE. This work has been submitted to 2022 TRB annual meeting. At the limit of the time, I will not show more details here. Now, we can provide the entire framework of our simulation platform. As we want to provide open source platform, we used SUMO as the traffic simulation and the Kala as the autonomous driving simulation, which integrates with the AutoWheel as the high fidelity AV models. To generate high fidelity traffic environment, we integrated our data-driven NDE modeling method with SOMO. The entire platform is open source, and we will release our codes in the near future. Here is a demonstration of the simulation platform. As you can see, AVs can drive in color where camera, radar, and LiDAR are supported, and different weather conditions can be tested. The traffic are generated by our NDE modeling method integrated in SOMO. And all the vehicles in color and SOMO are synchronized together. The AVs and the generated traffic can also interact with each other. So that's the demonstration of the simulation platform. To validate the effectiveness of our NDE modeling method, we collected the trajectory data of the simulations and compared with existing traffic models. The top two figures denote the distribution of vehicle velocity and relative distances. The blue one denotes the empirical distribution from the NDD, and the orange one denotes the simulation results. The bottom two figures denotes the well-known traffic models, including the Intelligent Driving model and with the 199 model used by racing. They were calibrated by the data from Virginia Tech and Shanghai, respectively. Comparing these results, our method can significantly better capture the stochastic and naturalistic driving behaviors of vehicles. We further test a simple AV model, which is combined of IBM car-fogging model and the mobile lane changing model. After about 25 million driving miles on the highway, the accident rate of the AV is estimated at about 2.01 times 10 to the power of -6 per mile. The relative error is smaller than 20%. So our simulation platform can evaluate the AV safety performance with much more accuracy. We also extend this framework to accelerated testing with scenario generation. As a rarity of accident, the simulation suffers from severe inefficiency issue. It has been pointed out that hundreds of millions of miles and sometimes hundreds of billions of miles are required to demonstrate AV safety performance. So the problem is how to generate testing scenarios to accelerate the testing efficiency. To illustrate the concepts of scenarios, we show two examples here. The left one is a simple cut-in scenario. Here, the blue vehicle denotes a background vehicle of the traffic environment, while the orange one denotes the AV under test. For a cut-in scenario, we need to specify the BV's cut-in behaviors, such as cut-in speed and relative distance. If we control the BV behavior according to the NDE models, the generated environment would be the naturalistic driving environment, which is good, but as point out, is inefficient for the safety assessment. Now, so the question is how to adjust the behavior model of BVs to accelerate the efficiency while keeping the accuracy. The right one scenario is another example of the highway driving scenario. Similarly, the behaviors of the background vehicles should be specified to interact with the AV and test the AV safety performance. Here, we only briefly illustrate the idea of the methodology for testing scenario library generation. The key is to identify a set of critical scenarios that can accurately and efficiently evaluate the safety performance of AVs. The basic framework is shown in the left figure. So here, each black circle denotes a specific scenario, and the small x denotes the decision variables of the scenario, such as the cut-in speed and the relative distance. All these black circles denotes the entire scenario space, denoted as capital X. So the basic idea is to evaluate the criticality of each scenario, and then identify the set of critical scenarios as the library. So here, the color denotes the criticality values, and the critical set denoted by the capital Phi can construct the testing scenario library generation library. Here are several challenges to make this framework be effective. For example, how to define the criticality function Phi V to generate critical scenarios that can accurately and efficiently evaluate the safety performance. How to determine the library Phi to balance the exploitation and exploration. How to handle the cost of dimensionality for high dimensional scenario X. And how to adapt different types of AVAs by the generated testing scenarios. So you can find more details in our series of papers recently published on IEEE transactions on intelligent transportation systems. Okay, now we can provide the entire framework of our simulation platform with scenario generation. After we obtain the high fidelity traffic behavior model, we further adjust the models to improve their testing efficiency while keeping the unbiasedness. Furthermore, I would like to briefly introduce our similar framework for the field test platform. The major differences are to replace the color by real test facility. In this study, we use MCT at the University of Michigan, and replace AutoWheel by the real AV. Here we use the L4 Lincoln MKZ hybrid vehicle. The simulation generated virtual traffic vehicles based on our NDE modeling method and scenario generation method, and sent this information to the real AV in the field test by wireless communication. The real AV can interact with virtual background vehicles in a synchronized way. For the AV, its driving environment is augmented with virtual traffic. So we called this platform as Augmented Reality Testing Platform. You can also find more details in our recent paper published on accident analysis and prevention. Here is a simple demonstration of the field test platform for cutting scenario. The left figure shows the MCD test facility, where the real AV is tested with the cutting scenario. Here is cutting the reason where the simulated background vehicle cut in, and the right figure denotes the print screen of the demonstration video, which I will show in the next slide. The top left denotes the augmented view of the AV, where a virtual vehicle is cutting in. Here, the red rectangle denotes the virtual background vehicle, and this one denotes the AV. And the top right denotes the view of the AV's front camera, where you can see that there is no real traffic vehicles in front of the AV. The bottom right figure denotes the simulation view, and you can see here the red vehicle denotes the background, the virtual background vehicle, and the yellow denotes the AV. And also this part denotes the parameters of the scenario. Okay, so let's see the demonstration video now. Here, we only show 3 representative cases, including no crash, near crash, and crash. So from this top left, you can see that a virtual background vehicle is cutting in front of the AV, and the AV can respond to the virtual background vehicle. So here are the relative distance and the relative speeds of the 2 vehicles. And this scenario is a near crash scenario, and you can see that a virtual background vehicle cutting in with a smaller relative distance and a larger relative speed. So the AV has a smaller time to respond. Okay, and okay, the last one is a scenario with crash. And here you can see this is the real camera view. You can see there's no real background vehicles. And this is a simulation view. You can see there is a virtual background vehicle cutting in front of the AV. So that's the basic idea. Okay. So here are some representative publications related to today's presentation. Oh, finally, thanks to my collaborators, Dr. Henry Yu, Dr. Yi Hengfeng, Dr. Yi Zhang, and graduate students working with me, Xintao Yan and Hao Sui. Thanks to research sponsors, NISA, CCAT, MCT, and DD. That's all. Thank you.
Thank you, Shuo. I think you answered most of the questions in the chat box, which is a good thing if you upload the pre-recorded video. So I think, yeah, maybe we'll skip them to the next one. And if you have any other questions, all the attendees, just feel free to ask Shuo or Yihen, who has been working with Shuo on this project as well. Let me go to the next one. And Seihan, I'm going to unmute you. Give me 1 sec.
Yeah, thank you, Zuran. I think now you can hear me, right?
Yeah, please share your screen while I'm introducing you. So our next speaker, Seihan Yuchar. Dr. Yuchar is currently working as a principal researcher in intelligent mobility systems at Infotech Labs, Toyota Motor North America. He received his bachelor degree in computer engineering from Izmir Institute of Technology in 2011. He received his master and PhD degree in computer science and engineering from Koç University in 2013 and 2017, respectively. He's now working on intelligent transportation systems and analyzing the impact of connected vehicles on transportation safety and management. Seihan, have you? Yeah, it's great. Yeah, I can see your screen over there. Yeah, without further ado, let's welcome Seihan, Dr. Yuchar. Seihan, I'm not sure whether I pronounced your name correctly because I've been, pronouncing your first name instead of your last name. And we cannot hear you, by the way. Hello? Let me do this very quickly. Ask to unmute.
Yeah, thank you, Ziran. I think you need to do unmute again. Okay, thank you very much.
Right.
So yeah, now you can see my screen, right?
Yes.
Perfect. Let me start. Sorry for the delay. So this talk is entitled as Cooperative Anomalous Driving Behavior Detection and Management. And I want to give some side information. So this work is done in a collaboration with our collaborator, Hao Yang, from McMaster University. I think he has a talk at the end of this workshop. So you can find more detailed information about the management part from section manager to the city manager. So I will cover some part of his talk. So let me start. So normally in a presentation like this, the expected behavior is to start with an outline. So, but against to expected behavior, against to normalcy, I will start with a video. So that's actually the definition of the anomaly. So anomaly is defined as an action done in an unusual location at an unusual time. So an anomalous driving behavior, such as aggressive driving, is one type of anomaly. So this video shows how dangerous the aggressive driving is, how big problem it is that we should solve as soon as possible. So let me play the video. So assume that you are driving that white Lexus and suddenly you recognize a tailgater. So this guy makes you stressed and he's chasing you intentionally. So the best thing that you should do is change lane and give right of way to that tailgater. However, this actually solves the small part of the problem, and this guy is still on road and threats the others, innocent people's safety. So as you can see in the video, the black car is somehow tailgating the white Lexus. And at the end, white Lexus change lane. And sometimes you can initiate tit for tat, a game, as you see the white Lexus intentionally brake. So now it gives the right of way to get rid of this tailgater. So let me first start with the problem definition. So our problem definition is innocent drivers are at an increasing and societal risk from anomalous, more specifically, distracted and aggressive driving behavior. So when we look at the status report on road safety, it can be observed that our problem statement is unfortunately correct. 55% of all fatal accidents are caused by the aggressive drivers. And rear-end collision are the most frequent type of collisions, and 87% of them are caused by the distracted driving behavior. Despite vehicles are enhanced in terms of advanced driving assistance and active safety management systems, these systems are kicked in when the driver has anomalous behavior, and they do not cover when nearby other vehicles behave abnormally. Moreover, these systems generate in-vehicle alerts for abnormal driving behavior. For example, the driver is notified as "you are get distracted," and they do not provide control suggestions to mitigate the negative effect of anomalous driving. So we want to address the abnormal driving behavior, and our solution is as follows. So in our solution, connected vehicles form a group to collaboratively track and identify the driving behavior of others. As seen in the figure, the gray vehicle is tailgating, and the connected vehicles in its vicinity conclude that it's an aggressive driving behavior. The detected aggressive driving behavior is then given as an input to the anomaly management. And the anomaly management generates control suggestions to save the lives of innocent drivers against the anomalous driving action and events. So this talk focuses on these two aspects, anomaly detection and anomaly management. So in cooperative anomaly detection, the first vehicle detects the abnormal driving behavior, becomes the controller, the leader, and it invites nearby connected vehicles through the vehicle-to-vehicle or vehicle-to-X communication to form a cluster for cooperation. The cluster members invite other vehicles and/or road users, possibly multi-hop away, and coordinate their sensors and/or resources to focus on anomaly. The cluster members share their speed and distance to collision measurement with controller, with the leader, and the controller decides if the observed driving behavior is abnormal or not. To classify the driving behavior as aggressive, we train a neural network-based machine learning model and use it to classify the observed measurement. The classification can be performed at the section manager, which may be located at the edge or cloud layer, or set of vehicles can be represented as virtual section manager, and the controller, the leader vehicle, can perform the driving behavior classification. In the management, we propose a severity-aware anomaly management. When an aggressive driving behavior is detected, the severity around the abnormal driver is levelized and called as anomaly severity index. The severity of anomaly may depend on many factors. For example, the type of anomaly or the time that the innocent drivers may react to, may react are the two important items in terms of severity levelization. We propose static and dynamic severity index, where the dynamic severity index depends on such kind of parameters like type of anomaly or predicted traffic congestion. And the static severity index, on the other hand, depends on the distance from the origin of anomaly. So in our evaluation, we implement the static severity indexing, and severity around the anomaly is levelized for each 200 meters. According to severity index, immediate lane changes, speed advisories, and reroute instructions are generated and shared with the innocent vehicles to dampen the negative effect of aggressive drivers. So in our simulation-based evaluation, we model I-66 route near Northern Virginia. The road network consists of 583 intersections and 38,000 vehicles in the morning peak hours. We assume that 17% of vehicles are connected vehicles and 5% of all vehicles behave abnormally. We collect realistic driving data through AIMSON and perform our simulation-based evaluation in OMNET and vehicles in network simulation weights. OMNET is a packet-level network simulator, and WANES is a tool where we can simulate different vehicular network topologies with advanced vehicle-to-X channel models. So these three simulators are integrated with each other to perform realistic driving behavior and realistic driving actions. In terms of modeling, it has been shown that car following behavior is significantly impacted when the drivers show anomalous behavior. For example, aggressive drivers react quickly to speed change of leaders, the preceding vehicle, and maintain smaller space compared to the normal behavior. Similarly, when the driver is distracted or under the influence of alcohol, misjudgments and/or inconsistencies are detected in terms of relative spacing. We have modeled two types of aggressiveness, periodic and random. Driver either behaves aggressive periodically or become an aggressive driver in a random manner. For example, one of the vehicles cuts your lane without signaling. So let's first look at the impact of abnormal driving behavior on vehicles. So these two figures represent the speed profiles of vehicles in a sparse and dense intersections. Blue lines are the normal vehicles, and the red lines represent the abnormal drivers. So when we look at the graph, we can claim two important observations. First, the abnormal driving behavior is propagated to all vehicles in its vicinity. It's really hard to point which vehicles is abnormal in figure B, right? On the other hand, it's straightforward for figure A. The impact created by the driver's abnormal actions may vary significantly according to traffic density. These graphs represent the performance evaluation of cooperative anomaly detection. We randomly select 10 intersections to see the detection rate of aggressive drivers. Overall, in 583 intersections, aggressive drivers are detected through cooperative anomaly detection by 17% of connected vehicles with an average 75% accuracy in three-hop collaboration. As the hop number increases in collaboration, more observation, more data can be collected, which provides better accuracy in terms of detecting the origin of anomaly. The detection accuracy, on the other hand, degrades in highly dense intersections in terms of detection of the origin of anomaly. As we explained in the previous slide, the abnormal driving behavior is contiguous in high dense intersections, and all of the vehicles somehow behave like abnormal. So in terms of anomaly management, we analyze the speed values of the current follower and leader preceding vehicle. The speed analysis of with management and without management cases are represented in these two figures. In without management, aggressive drivers accelerate unnecessarily, and this behavior is propagated to innocent vehicles. The red rectangle in without management case show that risky behavior of the innocent drivers. In with management case, on the other hand, the anomaly management generates speed and lane change advisories to mitigate this effect. The number of cases in the risky area on the green rectangle is decreased. Another key observation in anomaly management is, in without management case, the aggressive drivers are among the road participants. In other words, these drivers are almost uniformly distributed through all vehicles in different speed values. This can be observed in the red rectangle in without management case. In with management case, on the other hand, the aggressive drivers are shifted to the top left. In other words, the anomaly management separates the innocent drivers from aggressive drivers by giving proper and prioritized control suggestions. Through the generated control instruction, the proposed scheme prevents normal drivers to be part of anomalous driving behavior. The last observation is, in without management case, the aggressive driver's action are inherited by vehicles, and time to collision among vehicles is violated many times by other non-anomalous vehicles. With management case, on the other hand, the generated control suggestions help vehicles to keep safe distance and tied together on the center of the graph. As it can be observed, more concentrated points are in the middle of the graph in the with management case. So in addition to the leader and follower speed analysis, we compare the time to collision violation of all vehicles in different settings and under various control suggestions. The time to collision values are collected for all vehicles in Aimson simulation, and we demonstrate that with cooperative anomaly detection and management, 10 times safer transportation is possible. The detection triggered anomaly management instruction dampened the time to collision violation and error propagation to the other non-anomalous vehicles. Another important observation is the overall safety, including connected and non-connected vehicles, can be achieved by just controlling the connected vehicles. The generated instructions for connected vehicles somehow propagated to non-connected vehicles indirectly, and the overall safety is increased. So while working on this research track, as a conclusion, we have hard times in the definition of the abnormal driving behavior. So there's a subjectivity in the definition, right? Every driver may have their definition of anomalous driving behavior. The definition of the driving behavior and difference of itself can also be a good metric to come up with alternative solution rather than first defining the normal behavior, learn the abnormal driving behavior by comparing it with learned normalcy, which we propose in this talk. Moreover, we are interested in how we can change the driving behavior and or habits of people. One alternative solution we are seeking is, can we manipulate the behavior of connected vehicles to mitigate the negative effect of the abnormal driver? So as feature work, we want to extend the proposed system to test on different types of abnormal driving behavior and perform some sensitivity analysis in terms of overall delay and the benefits. So this concludes my talk. Ziran, could you please take over to lead the question?
Sure. Thank you very much, Sehan.
Yeah, thank you.
I think I will just pick out two questions.
Sure, go ahead, please.
The first question is coming from, I think, David, and I think I know the answer to that. So why did you choose a CV penetration rate of 17%?
Yeah, that's a good question. So this is the penetration rate of Toyota cars in the California. So we heuristically set 17%, but I'm sure in the Professor Hao Yang's presentation, you will see different connected vehicle penetration rate in terms of evaluation of the distracted drivers.
Mm-hmm. Okay.
I'm the co-author, collaborator with him, by the way, as I pointed in the beginning.
Thank you.
Go ahead, Zira.
And I think the second question is aligned with the first question. So the assumption is that all the vehicles are connected vehicle, and I think it's not right, 17%, right?
Yes. Could you please repeat the question?
The assumption is the assumption that the vehicles are all connected vehicle?
No, actually not. We assume that 17% of vehicles are connected, and the other assumption is connected vehicles can use their sensors to measure the behavior, the metrics of non-connected vehicles.
Mm-hmm. Thank you.
So we have non-connected vehicles, even we have non-connected and abnormal vehicles as well.
Thank you, Sehan. For the attendees, if you have more questions for Sehan, please feel free to ask in the chat box so he can answer. I
will try my best to answer all of them in the chat box. Please feel free to comment or to give an observation or future direction. I will be more than happy to listen.
Thank you again, Sehan.
Thank you, Ziran. I'm
So
stopping sharing.
Yep, appreciate that. Our next presenter, Mingyuan, if you can share your screen, start to share your screen right now. And you can unmute yourself. I think I give the permission to all the attendees. Mr. Mingyuan Yang is currently a PhD student in transportation engineering at UC Berkeley and a graduate student researcher at California Path, supervised by Dr. Xiaoyun Liu. His research mainly focuses on autonomous vehicles, freeway management strategies, and fuel consumption and emission modeling. And a request for all the attendees, if you have any questions, when you ask in the chat box, it will be great if you add a tag, so add somebody, at Zheran or at Seihan or Mingyuan, so it's easier for all the people to see whether which people this question will go to. I will hand it to you, Mingyuan.
Okay, thank you. So today I will talk about quantifying the environmental benefits of capacity enhancing traffic management strategies using microscopic simulation. I'm Mingyuan Yang from UC Berkeley. So in the near future, vehicles will be equipped with cooperative adaptive cruise control named CACC to allow them travel safely with short headways at higher speed, hence achieving higher capacity, alleviating congestion, and improving fuel economy. However, similar issues such as bottlenecks caused by frequent merges from freeway entrance will diminish the freeway capacity and the fuel economy benefit of connected and automated vehicles. Traffic management strategies such as freeway metering and variable speed advisory have been commonly used to enhance freeway capacity and reduce delay at bottlenecks near merging on-ramps. This study is trying to quantify the potential environmental benefits of implementing RAM metering and variable speed advisory on freeways with varying market penetrations of CACC vehicles. To realize this goal, a simple, accurate, and efficient fuel consumption model is extremely important, and there is also strong demands for recommendations and guidelines regarding the most accurate model to best estimate fuel consumption and emissions in traffic simulation and also in real-world traffic. Therefore, some preliminary works have been done in terms of comparison and validation of vehicle fuel consumption models using real-world data. The field experiments were conducted near Florida Atlantic University, organized by Professor David Kahn. So let me first introduce the experiment design of this work. We used the 3 test vehicles. All of them are compact vehicles to build a test, and each vehicle is equipped with the adaptive cruise control system named ACC system. The ACC system makes sure that acceleration and deceleration applied during the field experiments stay relatively consistent and free from random errors. 4 test scenarios were created to evaluate the performance under different traffic conditions. In detail, they are uninterrupted flow condition, represent cruising at the speed limit of 65 miles per hour for both low density and high density conditions. The interrupted flow represents the cruising at the speed limit of 35 miles per hour to mimic the traveling at arterial roads. The speed fluctuation stage represents during cruising the imprudent decelerations following with the acceleration back to the cruising speed at both freeway and the airport recirculation road. The 4th one is the stop and go traffic condition, represents following the vehicles picking up, dropping off passengers of the curbside roadways. Here are 2 plots that illustrate the test routes under different test scenarios. The testing route includes 2 parts. A segment of limit access the freeway, which is I-95, and the airport's roadways. So the test vehicles were driven along the I-95 northbound towards the airports and then circling along the curbside roadway and the recirculation roads of the airport for 4 rounds, and then back to the I-95 southbound. These 2 plots represent 2 different experiment settings. The experiment set 1 contains more test scenarios that I mentioned before, including the A1, B, C1, C2, and D test scenarios, while the experiment set 2 contains only 2 test scenarios, A2 and B. So experiment set 1 has more speed fluctuations, as you can see from this speed time chart. So as for the data collection part, 2 different sets of experiments I mentioned in the last slides are conducted on 12 different days, each set of experiments on 6 different days and under very different weather conditions. The field data collected via a data logger compatible with the OBD2 standard, and the data collected are in 0.2 second granularity and synchronized with the timestamps provided by the GPS units equipped on the vehicles to track the speed data in the correct time of day. 3 parameters were collected from the data logger. They are speed, engine revolutions per minute, and mass airflow rate. The speed data serves the most important input of all the 3 energy consumption models, while MAF and RPM readings calculate the benchmark fuel consumption. We cannot obtain the acceleration data directly from the data logger, so we approximate it by speed data. So the 3 different energy consumption models we compared here are all commonly used by the public, including the motor vehicle emission simulator model, named the MOVES model, the Virginia Tech Comprehensive Power-Based Fuel Consumption Model, named VT model, and the autonomy model developed by the Argonne Lab. 2 performance measurements, evaluation measurements are adopted in this study. They are mean absolute errors, named MAE, and the root mean squared error, named RMSE, to evaluate the performance of these 3 different models compared with the benchmark fuel consumption. So here comes to the results. The data collected in these 12 different days under 2 experiment settings. Here I just picked 2 typical days among these 12 days under each, so 1 day under 1 experiment setting. So they are April 7th and July 17th respectively. And the following 2 plots show the time-based fuel consumption patterns under 2 different periods: the free flow cruising period and the congested period. The curves in different colors represent different models. So in detail, the blue curves represent MOVES model, the orange curve represents the VT model, the red one represents autonomy model, while the green one represents the benchmark fuel consumption. So as we can see during the free flow cruising stage, as the left plots, all the 3 models actually share quite similar characteristics, which I will mention more in detail in the following slides. While the autonomy model performed the best among the 3 models, as we can see directly from the plots. As for the low speed and frequent stop and go conditions, as the right plots, the autonomy model still can provide a better fuel consumption estimation and capture most of the high and very low fuel consumption points. The MOVES model can give a very similar fuel consumption fluctuation pattern as the autonomy does, but it can give only a very limited numbers of values due to its way of using operating bins to calculate fuel consumption, while VT model is the worst one at this stage. So similar findings can be found from experiment setting 2, except that fluctuation of fuel consumption on this setting is much larger than the previous settings, which is consistent with the significance of speed fluctuations. So let's summarize the findings from these graphical results. During the free flow cruising stage, all three models share very similar characteristics, while autonomy performed best. But they are all prone to errors caused by minor speed fluctuations, and they are capable of capturing most high fuel consumption incurred by the imprudent speed changes, and they all slightly overestimate fuel consumptions at other situations. While during the low speed and frequent stop and go conditions, autonomy model provides better fuel consumption estimations, capture most of the high and very low fuel consumption points. Most model provide a similar pattern as autonomy does, but give limited number of values due to its way of using operating beams to calculate fuel consumption. VT model is the worst one at this stage, as the fluctuation range is much smaller than the other two models, as well as with the benchmark fuel consumption. So let's come to the quantitative analysis. The RMSE and MAE have been used for all these three models to compare their performance accuracy with the benchmark fuel consumption. From our analysis, we can see that the autonomy model actually provides much smaller errors on average compared with VT model and the MOVES model. The MOVES model can perform slightly better, around 9% better than the VT model. And this is due to the autonomy model can successfully capture the features of fuel consumption under stop and go waves, and thus provide most robust and accurate results. Another interesting phenomenon is about if we look at the error variance of these three models. The error variance of the autonomy model is also much smaller than that of MOVES and VT model, indicating that autonomy is the most robust model that is least sensitive to wind, rain, humidity, temperature, while MOVES and VT model may need more calibrations of certain parameters for different weather conditions. It's worth mentioning that these preliminary results are valid only under the test condition in Florida. More comprehensive studies need to be conducted in future to get more generalized performance evaluation results that account for other conditions outside of Florida, like extreme weather, lower temperature, and so on. So let's come back to our main studies about the, evaluating the environmental impacts of different control strategies. We use the simulation microscopic simulation platform MSUN, and we collect second by second vehicle trajectory data from MSUN, and we use autonomy that can precisely capture the speed fluctuations and stop and go waves to do the analysis. So the driver behavior model we use in the microscopic simulation is called path model. It is used to simulate realistic car following and lane changing behavior that lead to capacity drop at freeway merge bottlenecks. This model has been proven, calibrated, and validated very well by real-world data in previous studies. The autonomy model is used to estimate the fuel consumption and emissions by simulating the powertrain dynamics of individual vehicles. This model has been validated for several powertrain configurations and vehicle classes using field data. So the red plot provides, can see that autonomy model can support various layers of different options for the emission and fuel consumption analysis, including different vehicle classes, different fuel consumption types, and different powertrain engines. The network we use in this simulation is SR99 network, which is a 30-mile freeway section of SR99 northbound corridor in Sacramento, California. Includes 16 on-ramps, 11 off-ramps with a speed limit of 70 miles per hour. The simulation lasts 6 hours from 5 a.m. to 11 a.m. in a typical day. The RAM metering activated from 6 a.m. to 9:30 a.m. Control strategies we test in this study include local responsive RAM metering, coordinated RAM metering, and variable speed advisory. The different levels of CCC market penetrations vary from 0% to 100% with 20% increments in each scenario. So here first comes to the traffic management strategies. These are 3 speed contour plots under different control strategies, including no metering, the CRM, the coordinated RAM metering, and the variable speed advisory. So the red region represents the congested areas. So we can see that the CRM can reduce this congested area with a very obvious plot. We can see that the congested area here on the second plot is much smaller than the first one. And also the VSA can also reduce this congestion area from this visualization, like at the bottom of this main bottleneck. So here comes to some numerical results. The left one is about the average speed for this simulated network among different control strategies, while the right plot represents the GHG emissions and fuel consumption, the average fuel consumption among different control strategies. In summary, local responsive RAM metering could achieve about 5% mobility and 2% emission and fuel consumption improvement for the whole freeway corridor compared to the no metering case, while the coordinated RAM metering and variable speed advisory both achieved around 20% improvements in mobility as well as emission and fuel consumption, while coordinated RAM metering works slightly better than variable speed advisory alone. While we also tested different levels of CCC market penetrations from 0% to 100%, these 6 contour plots shows different CCC market penetrations, and we can see that the mobility performance of the corridor gets better and better as CACC MPR goes higher, and congestion disappears after CACC reaches 60% or higher. While for the numerical results, as CACC market penetration goes higher, the average speed is higher and the delay is lower. However, an interesting phenomenon is that when CACC goes higher, the emission and fuel consumption actually decrease first, but then increase after CACC MPR reaches 60% or higher. The potential explanation could be that the average speed gets higher while there is no congestion at all. Because from the last slides, we can see from the speed contours that the congestion basically disappears on freeway mainland after 60% CACC vehicles come in. And when there's no congestion and the average speed continuously increase, the fuel consumption and emissions can increase. So for the future work, right now, I just investigate the isolated effect of CACC vehicles and freeway management strategies. In future, we can investigate the combined effect of CACC vehicles and freeway management strategies and coordinate the implementations of RAM metering and variable speed advisory algorithms with these CVs. This work was sponsored by the US DOE department, and thank you. That's all for my presentation. Feel free to ask me questions.
Thank you very much, Mingyuan. Very good talk. Actually, I have 2 questions for you, if you don't mind. One thing is you implement all 3 different fuel consumption model, right? The MOVES model, autonomy, and Virginia Tech's model. So all this model were implemented as a post-processing kind of manner, right? You're not implementing them in real time and running in real time. Am I correct?
Yeah, not in real time.
Okay. So you first got the results from MSOM and then investigate that by running 3 different models.
Oh, actually, the data when compare these 3 different models are from the field experiments. So yeah, we have some vehicles in field, and we run these vehicles in field and collect some data like trajectory data.
But in the field implementation, you don't investigate the penetration rate, right? Because you don't have that many CACC vehicles.
Yes, that's right.
I see. Next question might be simpler. So I as far as I understand, all those vehicle types, they should be like ICE vehicles, right? There's no electrical vehicles or hybrid vehicles.
Yeah, that's correct. Yeah.
Do you have any plan to investigate EV or other vehicles in the future? Because that's a future trend, right?
Yeah. Because I would assume that the electric vehicles would have a very different fuel consumption and emission performance compared to the conventional engine vehicles. So if we can get some real world data from electric vehicles, we can calibrate those models specific for electric vehicles, and then running the simulations and adding those electric vehicles.
I see. Okay. Thank you. Thank you very much.
Thank you.
Yeah, that's all. For all attendees, if you have any more questions to Mingyuan, please feel free to add in the chat box. So David, you can unmute yourself and share your screen while I introduce you. So our next presenter is David Florence. Mr. Florence is an assistant research engineer at the Texas A&M Transportation Institute, or TTI. His expertise includes traffic signal systems and control, micro simulation, macro simulation, intelligent transportation systems, freeway operations, weather responsive traffic management, and traveler information systems. Mr. Florence specializes in adaptation of vehicle behavior in micro simulation for representation of connected and automated vehicle systems. So David, please go ahead.
Okay, good. I hope y'all can hear me. I'm trying to make sure I share the right screen here. I think
yes.
The best way to do it.
Yeah, it's the right one, and we can hear you.
Are you seeing the slide or the presentation view?
The full screen view of the slides.
Okay.
So it should be the presentation view.
Okay. So you're not seeing the next slide version or anything like that? Okay.
No.
Okay, great. That's funny. It has the icon on the other screen. Okay, great. Well, hello. Today I'll be talking about the Tosco system. This is a system designed by many different partners. This project is a federal highway funded project, and it's funded by the CAMP consortium of, and that stands for the Consortium or Crash Avoidance Metrics Partnership. It's a consortium of auto manufacturers, and they we have these. This is the current team. There are folks on the team that I'm covering. There were folks on the team of the project I'm covering today that aren't on this slide. There is Subaru and Volvo, and we also have UC Riverside that were involved in the research that I'm presenting today. This slide represents the current team. We have Honda, Ford, Nissan, Hyundai, GM, and Volkswagen. We have the Texas A&M Transportation Institute and UMTRI on the team right now. And I'll be talking about Tosco and how we're using VisSim to develop the system and evaluate how it's performing. So on this slide is the acknowledgement and disclaimer. Like I said, it's a federal highway funded project. And so here's the project number for you. And just a reminder that the findings and conclusions and recommendations are those of mine and not necessarily reflective of the U.S. Department of Transportation. So today, what I'm going to do is I'm going to give an overview of the Tosco system, talk about what we mean by traffic optimization for signalized corridors. I'm going to talk through the simulation that we have to represent the development of the TOSCO system and how we're using simulation to test the system and get some evaluation of it before we have it testing in the field. And then the simulations that we used to assess how TOSCO is impacting a corridor. I'll then go over some next steps, and then hopefully I'll have some time for questions at the end. So what is TOSCO? TOSCO is first and foremost a connected vehicle system. It uses DSRC communication using the standardized messages. This slide shows the infrastructure subsystem. So there are two different parts of TOSCO, the infrastructure and the vehicle end. TTI specializes in the infrastructure end of things, where we are essentially using the subsystem to communicate from the traffic signal controller, utilizing some vehicle detection in there, and using these two data sources to process information and prepare data for the TOSCO vehicle so they can better make decisions. Then you have the vehicle end of things. This, again, it's using DSRC, so there's an onboard unit that listens to those messages and then uses interface from the driver. You know, somebody has to turn on TOSCO, and then the TOSCO algorithm will then calculate a brake or acceleration command based on what decisions it wants to make on the approach to an intersection. And so what TOSCO does, and I'm going to have some slides to explain this part of the TOSCO system, but what TOSCO does is it essentially decides how it wants to accelerate or brake on approach to an intersection. The goal is to try to get through the intersection without stopping. So TOSCO has a few different tools at its disposal. We call these operating modes. As TOSCO is approaching the intersection, there are some key inputs for that TOSCO system. So first and foremost, there's communication range. DSRC doesn't communicate forever, or at a certain point, the vehicle enters range of that intersection and it starts receiving data. And so when it crosses that threshold, if you will, it's able to start making decisions. There's, of course, the point in time at which the vehicle crosses the stop bar. So once a vehicle crosses the stop bar, it changes its behavior because it's no longer approaching this intersection. And there are a couple of other inputs in there too. There's the set speed. This TOSCO algorithm is built on top of a CACC algorithm developed by CAMP. And what when it's outside of communication range from an intersection, it uses the set speed given to that TOSCO vehicle. But via the map message, we also get the speed limit of the at that intersection. So when the vehicle enters communication range, it becomes knowledgeable of the speed limit. And so in these next few slides, we have this graph here where the horizontal represents the time and the vertical represents the speed at which that vehicle is traveling. So inside communication range, there's the approach speed. This is where the vehicle is trying to decide what speed it wants to travel. And then after the vehicle crosses the stop bar, there's the opportunity for it to enter coordinated launch mode. This is where the vehicle is picking up speed and they all accelerate at the same time. So when the vehicles enter communication range, the first and most desirable operating mode is the speed up, at least from a mobility standpoint. This is where the vehicle enters communication range. The set speed is maybe a little bit lower than the speed limit, and so it's able to speed up to the speed limit and cross the intersection on a green light. So the idea here, the reason it speeds up from the set speed is so that any vehicles behind that TOSCO vehicle are able to get through the intersection, where if the vehicle had remained at the set speed, those trailing vehicles wouldn't have been able to cross the intersection. The next potential operating mode listed in the slides is the slow down operating mode. This is the case where the vehicle enters communication range on a red light, and the vehicle determines that if it slows down some, it could cross the intersection during the green light, the green indication. So then in the simplest terms, this is when the vehicle would slow down and cross the stop bar once the signal turns green. Slow down operating mode also considers cues. One of the detectors at the intersection calculates a queue length of the TOSCO algorithm, the queue length on each lane. so that the Tosco algorithm can decide how to respond to that cue. And then the other operating mode, or another operating mode, is the coordinated stop mode. So in this case, the vehicle enters communication range. It can't slow down in response to, it can't slow down and cross during the green indication. So the vehicle slows to a stop. So the idea here is that the vehicle can remain at its set speed for some amount of time and then slow to a stop at the stop bar, wait for a green light, and then perform a coordinated launch. And so the vehicle would pick up speed on its own. Coordinated launch requires some driver input because this is a level 1 autonomous system. The driver needs to tell the vehicle it's safe to launch. And the driver also needs to stay in the lane. So this coordinated stop will slow the vehicle to a stop gradually. Now, in the coordinated launch, what can happen if we have multiple Tosco vehicles next to each other is they'd all start moving at the same time. And so the idea here is that you increase the saturation flow rate, if you will, to throw a traffic engineering term in there, where you have more vehicles getting across that stop bar in less amount of time. So the simulation concept here, where we took this was we have different simulations that we're using to develop Tosco. This is true even to today, where we have simulations that are designed to test the infrastructure simulation environment. This tests those orange boxes that we saw on the previous slide, where we're seeing how does the Tosco algorithm, the infrastructure side of the Tosco algorithm, perform as it communicates queue length and other information, such as what we call the green window, that is the recommended time for vehicles to arrive at the stop bar. We're using the infrastructure simulation to determine how well the infrastructure is able to calculate those data elements and transmit to the vehicle. There's also the vehicle simulation environment. This is key in allowing us to test the Tosco vehicle algorithm before we have it on the runway. And so this is a algorithm developed from scratch, if you will. It's based on top of CACC, but all the different driving and operating modes were developed using or from scratch. So we needed to test, or it's desirable to test this before we get on the runway, so we don't spend too much time testing the algorithm or trying to figure out why this isn't working on the runway, where we could perhaps use simulation. And so that was really the concept coming in here. And the idea that the next stage, the third simulation that we use, is where we kind of pull together a revised vehicle simulation and represent it in a simplified way so that we can assess how Tosco impacts a roadway. In this presentation, I'm going to talk first about the vehicle level simulation environment and how the Tosco team was able to develop a simulation to represent how a real vehicle would drive so that we can develop Tosco in simulation and then test it at the field. And then I'm going to talk about the performance assessment environment, where we represent Tosco in a simplified way to calculate how Tosco is impacting vehicle emissions, fuel savings, or mobility on a corridor. So the vehicle level simulation involves 3 different computers. This is to help increase computation speed and also help us represent all the different facets involved with Tosco. So the first computer, perhaps the most important one from the Tosco standpoint, is the development environment. This uses the key piece of software here is the ADTF. It's a German acronym. I don't really know what it means, but it's a software that hosts this Tosco algorithm. It runs the decisions Tosco is making as if it's in a real vehicle. So of course, this is key to developing Tosco, because that's the exact software that we would then install onto a computer and plug into a vehicle so that Tosco could operate in the field. The other computer is the simulation environment. The key piece of software here is Simulink, the MATLAB product. What Simulink does is it prepares information for the Tosco algorithm running on the other computer. And it also calculates other variables to represent what's happening in the real world, like the radar sensor. It also represents DSRC communications. this simulation environment essentially packs everything and attempts to create a data flow representative of the field, so that when the Tosco algorithm on the other computer attempts to calculate, it has all the information as if it's in a real vehicle. And then finally, the other computer runs VISM. This is referred to as the traffic environment or even the driving environment, sometimes by the team, where this component hosts VISM, which generates the vehicles and produces that initial data flow, if you will, of where the vehicles are when they're generated. It also hosts the infrastructure component. This is the part that calculates the queue length, the green window, and other information for those Tosco vehicles as they are traveling along the roadway. This vehicle level simulation is designed for a single intersection, and the primary purpose of this is so that we can develop the Tosco algorithm without needing to take it to the field over and over again. It allows us to develop Tosco and have it ready, have what we think will work, and then take it to the field and test what we envision as close to a final product. So the way we do this, the cyclic process involved with developing Tosco involved defining a simulation where we're trying to see which part of Tosco do we want to test. Do we want to test the speed up? Do we want to test its ability to slow down or to come to a coordinated stop, and so on? This would then, involve the portion of the Tosco team developing software for that. There would be another portion of the team that develops a simulation environment of this scenario to run to evaluate that software. Once those step 2 and 3 are complete, there's the running of the simulations. And this involves, there's actually a member of the Tosco team that developed a software to run simulations over and over again at different introduction times, even, so that we could see how Tosco is behaving across time on the approach to an intersection, if they were arriving 1 second after another, if you will. We would then take the simulation results and plot them, visualize them so that the team can easily look to see, did Tosco do something strange here? We would document and analyze those results and say, hey, there's a change, there's a weird behavior here on this, at this introduction time, Tosco vehicles maybe didn't stop, or they maybe maybe crossed the intersection on the yellow, which the Tosco algorithm isn't designed to do. So the team would then identify changes, develop new software, and then repeat the process, so that we were able to test all these different scenarios and have the Tosco system, make refinements to the Tosco system prior to needing to take it to the field. And so some of the challenges and findings from this vehicle level simulation is that this was a great tool to perform some early refinements of that Tosco system to ensure desirable behavior in each operating mode. It was success. We had success in seeing the operating modes and making refinements prior to going to the field. Another finding is our initial speed profile definitions when we first envisioned Tosco needed some changes to them to handle initial accelerations. We found that some of the assumptions that we made at the beginning for those acceleration profiles wouldn't really work after performing some simulations. And so the team then developed some refinements there. That was one of the key refinements made to the Tosco algorithm. We're continuing testing to refine the algorithm. And so we're using different velocities, different speeds now as we generate those Tosco vehicles. We're even going to a different intersection in vehicle level simulation to see how Tosco vehicles are handling a curve these days. But back to the previous project, the other thing that we use, or the previous phase, after we had a good idea of how Tosco performed, we started the evaluation. And so what this did, we took from the Texas end, we took State Highway 105 in Conroe, Texas, and we that's our deployment target. We simulated 15 intersections along that roadway. The speed limits range from 55 miles per hour to 45. We simulated the AM and PM peak periods with different market penetration rates. This is a simplified graph of how we set up this VISM model for Tosco's evaluation. Within VISM, we use the emissions model DLL to get the MOVES model integrated into the software, so we had some idea of the changes in emissions. We used VISM to simulate the traffic. This involved the ASC3 controller so that we could get SPAT information, which is an integral information for that infrastructure algorithm to work. We then used a driver model DLL API from VISM to change the behavior of vehicles as they, and essentially in the driver model DLL held the Tosco algorithm, the simplified Tosco algorithm, for evaluating how Tosco impacts State Highway 105. So the driver model DLL generated our VSM data so that we had some sense of, the connected vehicle representation in there. Some of the challenges we had from the traffic level simulation is the synchronization between the different software, and we even had some challenges with synchronization between machines for the vehicle level simulation, ensuring that data flow was at the right time and all the data is represented between these different softwares proved to be more challenging than we had originally anticipated. The other challenge from another challenge from the traffic level end of things was comparing the Tosco behavior to the baseline traffic. We had some constraints on how Tosco could accelerate, and the representation of baseline traffic in VISM was much more aggressive than what we had for Tosco, and that created some real challenges in comparing the Tosco algorithm to the default driving behavior in VISM. We had some challenges in collecting unique performance measures, such as operating mode and speed trajectories, and even signs of oversaturation in the model. These were handled via generating other log files and using some indicators of these conditions for those Tosco vehicles. So the next steps, we're currently in Tosco phase 2 of the project. We're refining the vehicle algorithms and testing them further. We're preparing to build a test deployment on TTI's Rellis campus. That would be the first time it's actually scheduled for early next year in 2021. This would be the first time that we're seeing the infrastructure algorithm and the vehicle algorithm all working together in one place. So it will be a very exciting set of testing early next year to confirm Tosco's performance. And the team has integrated refinements to the Tosco traffic level simulation. We're now working to get a better representation of how Tosco operates in that traffic level simulation to improve our evaluation of Tosco on State Highway 105. And per funding from FHWA, the ultimate goal is to deploy Tosco on State Highway 105 and perform some field testing by the end of Tosco phase 2. So with that, thank you for your attention, and I'd be happy to answer any questions.
Thank you very much, David. So I think a question came from Saham is that what is your vision in terms of such kind of infrastructure availability and support in near 5 to 10 years?
Yeah, that's a good question. It's a loaded question. Tosco does involve a number of sensors. Like I said, we need to know the queue information on a lane-by-lane basis for Tosco to operate at its best. We also need some SPAT information. We've reached out and we're actually involved with the IOO OEM forum. So we've been talking quite a bit with infrastructure owner operators and obviously the vehicle manufacturers on the team about how Tosco would operate. We've seen great interest from both parties throughout this process. So we're hopeful. Again, it's kind of hard to project in the future what kind of interest we're going to have from infrastructure owner operators. But as we continue to prove that Tosco performs well, then we think that Tosco has a really good opportunity. Actually, we're using off-the-shelf sensors for determining the queue lengths. So the technology exists today for TTI's approach for developing all the information for Tosco. I've actually seen these sensors throughout Texas, and so some folks have even started picking up some infrastructure owner operators have already started picking up the sensors, and they'd only need to update their ability to broadcast the SRC information to get Tosco to work in theory.
Okay, thank you. One following question actually I have is, the Tosco algorithm or the whole architecture, does it require the communication to be DSRC, or it might be also suitable for, say, CV2X? Because I know, as far as I know, Ford, they are a major contributor or advocate of CV2X. So what's the vision of this project in the future in terms of the communication technology?
Right, yeah. Wow, that's another interesting question. I will say that CAMP, we're in the Vehicle to Infrastructure DSRC Consortium. So Tosco has been completely discussed from the mindset of DSRC communication. I would need to talk with the CAMP team about the possibilities of cellular V2X. It depends on how the system performs ultimately. Tosco isn't necessarily married to any communication medium, but up to this point, we've been only discussing DSRC.
Got it. Thank you again, David. So if you have any more questions to David, please feel free to add in the chat box. Thank you, David.
Thank you.
So our next presenter is Godong Rong. Godong, can you please share your screen?
Yeah.
Dr. Rong is currently a principal engineer at LG Silicon Valley Lab, working on simulator for autonomous vehicles, i.e. LG SVL. Before joining LG, he was a principal engineer at Baidu USA, a principal architect of VR/AR at Huawei Technologies, a senior software engineer at Google in YouTube VR team, a staff research engineer at Samsung Research America, Silicon Valley, a senior system software engineer at NVIDIA, and a postdoctoral researcher at the Department of Computer Science, University of Texas at Dallas. Dr. Rong received his PhD degree from School of Computing, National University of Singapore, and a master and bachelor degree from School of Computer Science and Technology, Shandong University. Please go ahead and present the exciting work, Godong.
Okay, so you can see my screen right now.
Yes, and we can hear you clearly.
Great. Good morning, good afternoon, good evening, everyone. So I'm Godong Rong from LG American R&D Lab. So today I'm going to present our simulator named LG SVL Simulator. So LG SVL stands for LG Silicon Valley Lab, which is the old name of our lab. And first, why we need simulator for autonomous driving? I think all the people here, we know very well why we need it. I just quickly go through some advantages of simulator. So they're fast, so we can drive billions of miles in parallel on cloud, and it's safe. So there's no critical life-threatening accidents involved. And particularly nowadays, it's a COVID-19 pandemic situation. So it's very difficult or impossible to drive the real car on the road to do the test. So, but we can still use simulator to test our AD software. And it's cheap. So for many developers, they don't have a physical car to test their algorithm, but they can use a simulation to do that. And it can get better coverage of many different properties, like different time of day, different weather condition, road condition, as well as lots of corner cases, traffic where it's very difficult or impossible to meet in the real world. And finally, but not least, last but not least, it is a very good tool to generate synthetic data, which is automatically labeled data with ground truth, where some ground truth is difficult or impossible to be manually labeled. And this diagram shows the scope of our simulator. As you can see, the middle blue box is the scope of the AD stack, and the left and the right two red boxes are the scope of our simulator. On the left side, so we simulate all environment, virtual environment, including the buildings, road network, traffic system, non-ego car, we call it NPC, non-player characters, and pedestrians, and different time of day, weather, etc. So all kind of environment. And also we simulate all kinds of sensors. So we have camera, LiDAR, radar, GPS, IMU, and lots of logical sensors. And also we generate HD maps used by the AD stack. And on the right side, we also simulate the vehicle dynamics to use the controls command from the AD stack to drive the Eagle vehicle. And our simulator communicates with the AD stack via some bridge. And here is an overview of all the modules in our simulator. As you can see, we have lots of pink modules to support different functions, which communicate co-working with the blue modules, which are the customer modules, including AD stack and vehicle model, sensor model, etc. And we also support third-party environment and third-party scenarios. And here is a full list of the main features of our simulator. So our core simulator is fully open source on GitHub, and it is Unity-based. It has a HDRP render pipeline, and it has lots of sensor simulation, including camera, LiDAR, radar, GPS, IMU, etc. And it can generate lots of ground truth via some virtual sensor, including 2D, 3D bounding box, semantic instance segmentation, depth, and landline information, etc. And we have implemented some bridges for ROS and CyberRT support. So you can use the Apollo and AutoWare, which base the CyberRT and ROS respectively. And we support many different HD map formats, including OpenDrive, Landed 2, Apollo HD map, etc. So, and also we have a full set of Python API. You can write the scripts to communicate with our simulator to control different factors, properties in the simulation. And based on that open source simulator, we also provide lots of premium features to make this more powerful for the real user use our simulator in their real production or researches. So this feature included distributed simulation, digital twin generation from recorded data, scenario generation, and simulation on the cloud with CI. So next I will introduce all of them in details. But first, let's see this video. So this video shows the rendering results of our simulator. But thanks to the HDRP render pipeline of the Unity, so we can generate very realistic rendering result. So with different various of the environment variables. And this video demonstrates more variables like different levels of fog and different levels of wetness. So you can see the reflection on the road and different time of day, the daytime and nighttime, etc. And this video is recorded, I think, several months ago. So we now have much better result than this one. And as we said before, we have simulated a lot of sensors. So the first, here it shows some examples. The first row shows some physical sensors, like you can see on the real autonomous driving car, like camera, LiDAR, radar, etc. And the second row is what we call the logical sensor or virtual sensor, which can generate the ground truth. Like what we see here is instant segmentation and depth message and 3D bounding box. But we have lots more. And we also have a way to allow the user to write their own sensor plugin to implement more complicated sensor. So here is our example of Validant LiDAR sensor plugin. It can generate raw data matching the Validant LiDAR models, VLP16, VLP32C, VLS128, etc. And because it's in the same format of the real Validant LiDAR, so the raw data can be used by Validant driver and Validant tools. So this is Validant the viewer to view the point cloud generated by our sensor. And our simulator is out-of-box support with lots of AD stacks. Particularly, it supports the two most widely used open source AD stack. The left is Apollo from Baidu, and the right is AutoWire from the AutoWire Foundation. So when I say out-of-box support, means you can simply go to our website, download our latest binary, and run our simulator. And then you can clone the latest Apollo or AutoWire from their website. You don't need to do any change. You can just run Apollo or AutoWire, so it will automatically work with our simulator. The bridges are all included in their latest version. And by the way, we are the founding member of AutoWire Foundation. And because our simulator is already integrated in both Apollo and AutoWire, so I would say they have already been the de facto default simulator for both of them right now. And in addition, we have the open plugin scheme. Because we cannot support everything, so we understand that. So we have this plugin scheme allowing the user to write their own plugin to expand the functions of our simulator. As I said before, we have sensor plugin, and the Validant LiDAR is just one example. And we currently have the built-in ROS tool and CyberRT bridge. But if the user is using their own middleware, so you can write their own bridge plugin. And for the dynamics, we have the FMI, so functional mockup interface. The user can write their own functional mockup unit to use their own dynamics algorithm. So here's a video from a company named Best Media, where they use our simulator together with CarSim to get a better vehicle dynamics. And we also have the NPC behavior plugin. So user can write their own plugin to control the NPC to get a better traffic simulation. So we have some plugins examples like the lane follow plugin, waypoint plugin. We also have a drunk driver plugin to simulate some aggressive driver. But user may want to write their plugin using Sumo or other traffic simulation to get better traffic simulation in our simulator. And also we have a controllable plugin. So basically user can write anything that's controllable, like traffic sign, charging station, the speed limit sign, etc. And we also have a HD map annotation tool. So you can manually annotate the HD map and output to lots of different formats, OpenDrive, Lenlit to Baidu HD map for the autonomous driving software to use. And we can also input all of them. So once we input the HD map, we can automatically generate a mesh for the road surface to generate a road network environment. And also we have a full set of Python API. So you can clone our Python API repo and use it to write your own Python script, which can communicate with our simulator to set up lots of properties during the runtime. And next is our premium feature. First is a distributed simulation. We understand that no matter how powerful your machine is, so that is impossible to simulate too much things. For example, if you have 10 cameras, 4 LiDARs on the Eagle car, because we support multi-ego car, and if you have lots of ego cars or even lots of NPCs, so it's almost impossible to simulate everything on a single machine. So that's a reason we have this distributed simulation, where you can use more than one machine to do one single simulation. So here is a video showing two machines, master and client. So several sensors are simulating on master, but several sensors are simulating on client machine. But both machines are synchronized to perform one single simulation. So that's very important to get a real-time speed or faster than real-time speed for the complicated simulation. And we also have the digital twin service. So if you want to generate a digital twin of your own environment, you can drive the real car in your own environment, collect the data. So the main data will be the camera images, LiDAR point clouds, and GPS data. You upload data to our cloud service, and it will automatically generate a point cloud-based digital twin. We call it Digital Twin Lite. And if you want more, we can do some manual post-processing to generate a beautiful mesh-based digital twin. We call it Digital Twin Full. And here is the digital twin we generated at the Gomenton station, which is the AD test driving stack owned by AAA in Concord, North California. So we have collaborated with UC Berkeley to test it in Gomenton. Because you know that testing in Gomenton is very expensive and time consuming. So what we do is that we use Berkeley Scenic to generate thousands of different scenarios and test them in our simulation, in our simulator. And then we only choose 3 to 5 the most interesting scenarios and to test in the Gomenton real test tracks. So that saves lots of times. So by the way, the Berkeley has a paper together with us and AAA published on ITSC. I believe it will be presented tomorrow. So you can find more details there. And so as I said, we have the Python scripts. You can use it to write your own scenarios. The manually written scenario is always the not a good work. So we want to provide lots of useful tools for users to generate scenarios. For example, we have a real scenario editor. So you can just simply drag and drop cars and pedestrians and draw the past and how they define how they move and define lots of trigger events there. So, and finally, everything will be saved in the scenario script. And we also use the Scenic language from UC Berkeley to automatically generate thousands, no, tens of thousands different scenarios, concrete scenarios from a single abstract scenario. And then we also have a resim support. So resim means you can run the simulation and record everything into a scenario and replay it, but with some different properties. For example, this video shows you run the scenario in the daytime and record it, then you can replay the scenario at the nighttime. And last but not least, we have the cloud-based cloud simulation platform. So now we have built a full cloud support on AWS, but we can also deploy the cloud on the user's private cloud service if needed. And on the cloud, we have lots of the Docker container. So we have container for AD software like Apollo, and we have container for our simulator, which contains lots of instances of our simulator. And we have container for test cases. So all those containers interact with each other. So as a result, we can run thousands of different scenarios in parallel on cloud. And when they are finished, we can automatically generate a detailed report for you. So this, which scenarios are success, which scenarios failed. And you can analyze the result and find the most interesting scenarios and download it to your local machine for the further debug or testing. Okay, that's all our features. I will conclude my presentation with our value proposition. As I said before, so our simulator simulates everything the simulator wants to do. So we simulate a world, we simulate a vehicle, we simulate the sensors. Although we have a lot of features, but we understand that no one can do the simulation perfectly by themselves because the simulation is so difficult. So we want to build together with everyone an open community to build an ecosystem for everyone. This open means several-fold. So first, we have an open cloud simulation platform where everyone can upload their environment and can run their simulation on our cloud. And if they like, they can share the results to other teams in the community. So we will have lots of huge database to be shared by the whole community. And we have the open AD content generation. We provide lots of tools like the digital twin generation, scenario generation, map generation, etc. And the user can generate lots of, currently we have some building contents that we have about 10 different maps and several different vehicle models and lots of building sensors and lots of the default testing scenarios. But the user can create much more of that and share it with the whole community. And finally, as I said, our core simulation engine is fully open source on GitHub, and the user can enhance it using different kinds of plugins to satisfy their specific requirement. Okay, that's all of my presentation today. If you want to learn more about our simulator, so here are some links for you. And if you have questions or want to collaborate with us, you're welcome to write email to contact@lgsvillesimulator.com. And here is my personal contact information. You can also write emails to me directly. Thank you.
Thank you, Godong. It would be great if you can share that website, maybe in our chat box, so others.
Sure. I'll post the website and GitHub links and our emails in the chat box later.
Thank you. One question I have for you is for slide 15 regarding the digital twin. From what I understand for implementation, a digital twin here you mentioned is more like a parallel simulation, or it's like a virtual representations of what is happening in the real world, right? It doesn't necessarily mean there is a cloud or there is a server which is connecting to the simulation.
So digital twin is just a model of the real world. So it's just a replica of the real world. I mean, it's just a fancy word. So our digital twin service is just a fancy word of the service to automatically generate a virtual environment for you. So you can drive the car in the real environment, upload data, and we create a virtual environment for you.
So the video on the right, I see it's a little bit lower resolution than the original video.
This one is point-based, it's not mesh-based. So it looks badly to the previous video, but this point-based digital twin is fully automated. So no human body, no human work is involved. So this video is rendered by our point-based render engine. So you see although it's point-based, but there's no holes on the surface.
I see.
Although it's bad to human eyes, but it's good enough to the autonomous vehicle sensors, like the LiDAR and radar, etc.
I see. And one more question I have. So there's also bridges for like ROS or Apollo or external software, right? Which is developed by you, by LGSVL.
Yeah, we currently have built-in bridges for ROS2 and where do I list it? I think we currently have the ROS2 and CyberIT, 3 different bridges, all created by us. But because AutoWare.ai is based on ROS, AutoWare.auto is based on ROS2, and Apollo is based on CyberIT. So those are most widely used open source AD software. So we build those those 3 bridges as a default bridge. But if the user, let's say some user, they don't use ROS or SRBIT, they have their own kind of middleware. So they can also use their own bridge plugin.
Thank you. And 2 more questions. Sorry, I just see that from chat box. One following question, followed by my earlier one, is is this digital twin rendering engine available to public as well?
Yes. Yeah,
So
the
it's
digital
on the
twin
website?
creation is a premium feature, but once you have the digital twin, you can use it in our open source simulator. And in fact, I said we have around 10 different maps. Some of them are created by this digital twin.
Okay.
Including the Go Mountain. The Go Mountain is a very famous test track in North California. I believe many people will use the Go Mountain test track, so they can first test in our simulation and then only find some specific scenarios, then go to the real Go Mountain side to pay to drive in the real world.
And the last question came from Professor Chi Zhu. He asked, maybe we talked about this before as well, whether there is a way to simulate the V2X communication or plug in a network simulator in LGSVL.
Yeah, we can definitely simulate a lot more. So currently we only focus on the autonomous driving, but it's not only for that. We can definitely support V2X. And in fact, we have already some users use our simulator to do V2X and to do the smart, intelligent traffic control. Like they can put sensors, currently all the sensors attached to the Eagle car. But some of our users, they can put the sensor to the roadside, let's say attached to the traffic flight pole, to use that sensors to control the traffic or to do the V2X communication, V2I, V2V, etc. Yeah, so yeah, this simulator can be used by a lot of different things.
Yeah. Okay. Thank you once again, Gordon. If anyone else have any questions, please feel free to ask Gordon in the chat box. Thank you. So our next talk is going to be Mr. Dean Dieter. But before that, we might have a 15 or 20 minutes break where Chris can moderate this session and we can have some discussion over simulation, over whatever we have in mind. Chris, please go ahead.
Thank you, Ziran. Yeah, welcome everybody. And sorry that we can't all meet in person. It's really unfortunate. And since this is our coffee break time, normally we'd be filing out into the hallway and getting our cup of coffee and our cookie and doing a little bit of socializing and networking. And so if you are going to get your coffee, that's fine. But if you are still with us here during the break, I'd invite you to turn your video on if you'd like and introduce yourself to the group. I'll begin. My name is Chris Schwartz and I'm at the University of Iowa at the National Advanced Driving Simulator. So we're very interested in human-in-the-loop simulation. We have a very large driving simulator. We do a lot of work on automated vehicles. But we also have an exciting project on the road with an instrumented vehicle that will be focusing on rural environments. So roads that are not well marked, maybe even some gravel. So it'll be very interesting. And then after you introduce yourself, like I just did, I'd like to suggest that you drop a comment in chat because it'll make it very easy for people to follow up with you. So I'm going to do that right now. And then if anyone wants to, send me a message or start a private chat, you can do that. And moreover, if anybody knows what movie I just quoted, you'll have my undying respect. And you'll be able to let me know. So if anyone else wants to jump in, please introduce yourself. Let's spend a few minutes just doing that and getting some networking going.
Yeah, thank you, Chris. Maybe I'll take over for this. My name is Ziran Wang, and I am currently a research scientist at Toyota Motor North America, which is I'm the colleague of Seihan, who just presented. And in Toyota here, we are based in Mountain View in Silicon Valley, and we have been working on all different technology of connected vehicles, and doing simulations, doing modeling, doing real world implementations, and yeah, that's pretty much from my side. I see, David, you turn on your video. Maybe you want to introduce yourself a little bit more?
Sure, I'll go. So I'm David Florence. I'm obviously involved with the Tosco project, but at TTI I do all sorts of other simulations. I've simulated rural roadways for for roadway design type work. We do lots of different stuff at TTI, from emissions to roadway design to even crash tests. It's really exciting. I don't get to play with all that stuff, but I personally work quite a bit with DSRC communication and traffic simulation. Yeah.
Great.
Thank you.
Someone else jump in?
Yeah, I can go next. My name is Yihan Feng, and I'm currently an assistant professor at Purdue University. Actually, I just joined this fall. Previously, I was with the University of Michigan Transportation Research Institute. And actually, I was working with some of the presenters today, including Dr. Shuofeng, the first presenter regarding the CAV testing scenario generation, and also David Florence on the Tosco project. So my main research interests are the CAV-based traffic control, including the traffic signal optimization, vehicle trajectory planning, and also about emission and fuel consumption modeling. Now it's very nice to be here today and to hear so many great presentations.
Yihan, by the way, where you are at? You're in Michigan or in Purdue right now?
I'm in Purdue right now. Yeah, I'm in my office actually.
Oh, really? New office?
Yes, my new office.
Looks great. But are there any student over there or any professors over there?
Not many actually. Although we can access the building like freely, there's no restrictions. But not many people come actually.
Okay, but the courses are still online, right?
No, most of the courses are we provide this we call flexi, high flexi. It's like a hybrid mode that you can go to the classroom or you can stay online to listen to the broadcast.
Okay, but you will still do like in-person lecture?
Yes, I prefer to do that. Otherwise I can. I mean, in that way I can see the students' reactions, right?
Mm-hmm.
Otherwise, I don't know whether students understand me or not, and so it's been difficult. But it's been difficult.
Mm-hmm. Here in Iowa, we canceled spring break for the spring semester already.
Oh.
We're going to start classes a week late, and there won't be any spring break for anybody in Iowa.
Oh, yeah, I think that's the same for here.
Is that right?
For here too, right? To shorten the semester.
Wow.
Gordon, you want to? Yeah, Gordon, you want to go next?
Oh yeah, I just want to say hello to everyone. So because you just listen to my talk, you already know what I'm doing here. So yeah, I think that's as I said at the end of my presentation. So we know that simulation is very difficult. So there are lots of things to do. So although we have lots of features, but we totally understand it will not be enough. For example, the vehicle dynamics. So our current dynamics is relatively simple, and traffic flow, our current traffic is not that smart. So we definitely want the users can build more plugins to expand it. And of course, expand it to new usage, like the mentioned in the question, the V2X, smart traffic control, etc. And we also have some researchers collaboration on the security attack of the autonomous vehicle. They want to test how the autonomous driver behaves for the attacks, for the, let's say, attack for signal, for GPS signal, attack for LiDAR, attack for camera, etc. how they can behave well during an attack. So if you test that on the real world, it will be very dangerous because the attack may cause clearance. But if you test in the simulation, that would be good. Yeah, lots of new use cases we never think about before. So you're welcome to contact us to propose new usage. Yeah, because it's basically just a game. It's built by Unity. You can use it for a lot of things. People use GTA 5 before to, GTA 5 itself a game. Yeah, but people use GTA 5 for lots of simulation. But we're just building another more powerful games dedicated for autonomous driving.
Gordon, just one question. As I just mentioned earlier, so Unity just went public last Friday.
Yeah.
Do you have any collaboration? I mean, LG have any official collaborations? You get some profit as well? A share?
No, we do have some collaboration, but I don't think we can get any profit from their IPO.
Will it mean anything for you, really? Will it change? Will it change your
nothing to us, as far as I know. So, unless they want to increase some price, or I don't know.
Hello, perhaps I can say a bit about myself. My name is Qi Zhu from Northwestern University. I'm an associate professor there. I actually learned about this workshop from my student Xiangguo, who interned at Toyota last year. Was that last year, right? Yeah. So thanks Zhiran and others for organizing this. My research area is a little bit different. It's more on traditionally on computer engineering, and so we look more into, I guess, lower layer stacks in autonomous and connected vehicles. So mostly software, hardware. We did do some work in recent years looking into the security issues of connected vehicle applications, especially considering communication disruptions, for instance, jamming attacks, possibly spoofing attacks, etc. And recently looking into autonomous vehicles as well. So we're trying to sort of bridge some of the transportation layer study to the lower layer impact from your software, hardware, communication stacks. So that's our focus. So I'm really happy to attend this workshop and learn from everybody. Thanks.
Thank you. And Professor Zhu, welcome to the ITSS Society. I mean, you haven't been too much to like IV or ITSC before, right? Or you have?
No, not much. I mean, I know actually very recently, actually started from with Xiangguo. So Xiangguo has a paper this year at IV, and so he's, I think he's on the call as well. So he started sort of looking more onto the transportation layer and trying to get involved. We have other students working more at the layer of sort of single vehicle AV and both the security and also safety issues. So recently we have done some work on the safety of using machine learning in autonomous vehicles, especially not only on the perception, but also on the control planning and the decision making in general, using formal methods, some of those techniques. So we're hoping to somehow, perhaps in the future, to connect it with connected vehicles, and see whether we can sort of have more holistic view of some of the safety and security issues.
Sounds great. Thank you. Go in, you're in mute.
Sorry, yeah. maybe I can go to next. Yeah, my name is Guoyuan Wu, and currently I'm a researcher in the Center for Environmental Research and Technology at University of California, Riverside. Sorry, the long name. Yeah, I feel very honored to co-organize this workshop with Zan, Jiaqi, Yihen, and etc. Yeah, I think it's really informative, and I'm very excited to see all this great presentation from all of you, and also I really appreciate your approval to agreement to this to share your research. And for example, we actually, well, in what, beside, I mentioned that Zan, who is right now is in Toyota Infotech, and also Guodong, and we also have some close relationship, working together to develop some co-optimization, some co-simulation platform, something like that. So really appreciate. Yeah. So in our currently, I'm more more focus on this connecting automotive vehicle, but more from the sustainable or energy emission side. But we realize that with all this advancement of the modeling tools, it's really a time to dig into that, and then to make the whole modeling or the simulation more realistic or more sophisticated for our different purpose. Yes. Thank you. Yeah.
Great. Yan Chang, your video is on. Would you like to introduce yourself?
Yeah, sure. Nice to meet you all. I'm Yan from Lyft. I'm currently a senior software engineer at the path planning team, mainly working on the decision making, and last year mainly working on the trajectory generation. And before that, I actually working together with Professor Yiheng Feng at University of Michigan Transportation Research Institute, and also got a PhD there. Yeah, so today I'm very happy to really learn so many great new advanced technologies in the simulation field, and also in our daily life, we also use a lot for the simulation before we actually go public route. So yeah, really happy to meet you all, and also happy to do any collaboration if possible. Yeah.
Wonderful, thank you. And I think I missed, who are you with right now?
I'm at Lyft. We have, yes, we have a department called Level 5, which is dedicated for the development of autonomous driving. And also currently we also have a competition where we release the largest prediction data set, and we also have an award associated with that. So feel free to check it out. It's still open, and yeah, I would
Awesome.
also be happy to share more information related to that.
Okay, thank you. Jiaqi, you want to introduce yourself?
Sure. I guess you hear me, right? So my name is Jiaqi Ma. I'm an associate professor, University of California, Los Angeles. My work is kind of overlapped with everyone here who has except Dr. Qi Zhu. I don't do quite lower layer stuff, hardware stuff. Our focus can be described. We do cooperative driving quite a bit. The vehicles collaborate with each other, with infrastructure, how to design perception, control algorithms of the partial observable system to improve system efficiency and safety. So that's kind of our a quick description of work. And by the way, we have our version of Tosca, but it's kind of a simulation work. We're absolutely not at the scale of what the work that Tosca has been doing. It's glad to be one of the co-organizers. Actually, I was the original main organizer, but I kind of, because of the work Ziran took it over completely. I do appreciate it. Thank you.
How much time do we have, Ziran?
I think we can go ahead and maybe 10 more minutes? Yeah, we're fine. We're fine with the time limit because the organizer told us we don't have to finish by like in 1.5 hours. So we can continue to introduce ourselves.
In that case, maybe I can introduce myself.
Hi.
Hello, everyone. My name is LP. I am working at Chalmers University of Technology in Sweden. If not mistaken, those that I have heard so far are all in the United States now, right? Yes, okay. So then maybe there will be more coming from Europe or from other parts of the world here joining soon. Yes, just want to say that here at Chalmers, we are several people interested in the simulation as well. And at the moment, our interest is, well, I suppose it's quite wide, but at least we start with trying to understand what's the impact of deployment of autonomous vehicles, in this case, in the mixed traffic environments, mixed and heterogeneous traffic environments. Trying to understand how this transition period would look like, and maybe help to suggest cities and so on in their preparations. So we also start with our long history in the analysis of driving data, naturalistic driving data. So we take on board our knowledge from that analysis to work in this field now. But so far, we are pretty new as well in the simulation area. So we've been only exploring the use of Sumo. So I was very excited to hear also that this LG simulator that was presented today. So who knows if we will explore that as well at one time. Right now, we're just using Sumo because of, as you all know, it's open source, obviously. Nice to see you all.
Great.
Nice to see you.
I really enjoyed my visit to Gothenburg a few years ago. It's a beautiful area.
Yeah, maybe you were here for the IFE a few years ago.
It was
the intelligence vehicles, maybe? No?
It was the Fast Zero.
The Fast Zero, yes. The Fast Zero was also around that same year, yes. Mm-hmm.
Yeah.
Yes, that's nice to hear, yes. No, but yeah, if you come over again for any reason, I'll be happy to meet you.
Oh, would love that.
Maybe we can discuss some work.
Be able to travel anywhere.
Yeah, at the moment, no. At the moment, it's difficult, yes.
Yeah.
Although in Sweden, it's a bit more open than other parts of the world.
Well, that's good to hear.
Yeah.
Hi, Wei Min. Would you like to introduce yourself?
Hi, Chris. Nice to meet you. Nice to meet you to all. I'm a PhD student from Clemson University. I worked with Dr. Marshall Chaudhry. So our team is focused on connected and automated vehicles. So during my PhD program, I'm learning this cool stuff and the chat and the emerging transportation technologies. So right now, my dissertation research I include topics on freeway merging and the lane changing decisions for autonomous vehicles without connectivity. So yeah, I worked on 2 different simulation software that combines Sumo and the WebOps. WebOps is also can simulate autonomous vehicles. So to evaluate our decision-making strategies for in different traffic conditions. So yeah, I implemented the intelligent driver model and MPC controller for the vehicle controller. So I'm still working on it. So and from today's presentation, I learned a lot. It's really this topic for autonomous vehicle is very challenging. We hope we can have a very efficient connected and automated vehicle testing tools and the platform. I'm very glad to be here today. Just by the way, I'm looking for some researcher positions or postdoctor positions. If anyone is interested, I will leave my email here
yeah, my graduation will be next May. So I'm very excited to go to the next point. Yeah, very glad to see you all. Thank you.
You might want to share your CV over there.
Yeah, sure.
All right, who's next? Nils, would you like to introduce yourself?
Yeah, sure. Yeah, nice to meet you all. Nils Katzok is my name. I'm supporting the Europe side now, Selfie. I'm from Germany, so another one from Europe. I'm working for the site management in Immendingen, which you can see in the background. I just changed it recently, so I'm working for the new proving ground we built from Mercedes-Benz AG. So I'm more on the physical part of testing, less on the virtual part of side of testing. But it's also still a relevant part, of course. And yeah, it's very interesting to see how these pieces of virtual testing and physical testing will align. And I think we're experiencing that right now live, how these two areas come together. So it's very excited to learn a little bit more about the virtual testing side today.
Anyone else want to jump in?
I just have a question. Niels, do you know if that's the proving ground that you mentioned, is that as big as the one we have in Sweden here? The what's the name now? Now I even forget the name. AstaZero.
AstaZero, yeah, I know AstaZero, yeah. Hakan, I'm in contact with Hakan sometimes. I think it's from the area, from the acres, it's a little bit bigger. Okay. But it's not as big as other proving grounds since we have a small oval circuit. It's just 4.1 kilometers, I guess. Okay. Papenburg in Bremen or Nardo in Italy, they are much bigger than ours. But still, we have a lot of other modules like test area just for automated driving systems. So that's new. Okay. But I think it's a little bit bigger than AstaZero, yes.
So what is the special thing about this AD system? The part for testing AD system. I mean, why? Well, you mentioned that, so I guess there is something special that, at least compared to the standard proving ground. So could you describe a little bit?
Sure. So we installed some more infrastructure that is not that is on no other proving ground on the earth, as I guess, like the 3D target mover system from Messring. I think there have been some papers about that one. We just use that right now. We just started using it now, so it allows to test intention recognition from pedestrians and cyclists. So we can move our targets in all directions in three-dimensionally. And also the asphalt surface is very flat, so we can use all the GVD targets, the global vehicle targets, perfectly on them. So it's 10 hectares area. It's the one, that one.
Just behind you there. Yeah, okay, good to know. Thank you.
It's really neat. AstaZero is a really beautiful test track, though.
Yes. If I suppose some of you who have been here for some of these recent conference, like the IFE and so on, then you have been there because we have arranged a visit to AstaZero at the same time at the time.
You're focusing on automation of the testing actually a lot in AstaZero, right? That's pretty interesting.
Yeah, well, AstaZero, I suppose we try to be general in this case, that there are different areas for testing different things, including, of course, the autonomous driving in this case, and that has been used for this purpose recently as well, for different experiments, not just for the tests that are done by the Swedish partners, but even for other organizations from outside Sweden as well. But I mean, of course, there are still a lot of things as well that could be added more, for sure. I mean, that's why I want to know when you said it is bigger, one thing is bigger than AstaZero. And then I wanted to know what was even more than what we have already here, let's say, from a technology point of view.
I think the size does not matter when it comes to
No,
proving ground. The kind of test tracks, that is what matters. And I also think high-speed driving, especially for automated driving, is not the trend anymore, or it's not the trend in general. So the question is, do you need a big proving ground?
Yes, it's the communication part could be very important, and then the potential of including special sensors for not just communication, but also let's say traffic light that can be assigned, and extra like that. That is really important. Also, the 3D map layers in this case for the areas. And of course, the urban and the city environment, urban and non-urban environments that could still be improved further as well.
Yeah, I think you need a good portfolio of different types of environments. So you need urban, you need highway, you need country roads, etc. Yeah.
Yes, exactly.
Probably starting to run a little short on time here. Let's see if we can get one or two more in. No, you guys, it's fine. I love this great discussion. Mohit, would you like to introduce yourself? Unmute. You're muted.
Sorry. Hi everyone, this is Mohit. I'm doing PhD in Trinity College Dublin. And I'm working on connected autonomous vehicle in mixed traffic, especially under low penetration rate, how we can improve the traffic capacity and like while taking care of the safety. So I'm in the second year of PhD, so I'm in the process of formulating the research questions. So it's very lovely to attend the conference and get few ideas.
That's wonderful. Great. Best of luck to you in your program.
Yeah, thanks. Yes.
Thank you, Chris. If you don't mind, we can go back to our presentation, and you can mention if we have any like extended, discussion afterwards.
Yeah, if everyone's interested in it, we can certainly continue afterwards.
Yep. Thank you. Thank you, everyone. Let's go back to the presentation. Let me share my screen. Our next presenter is actually uploaded the video, but he's online right now. I see him, and we can share your questions to him while this video is played. So let me share. Let me share one more time because I didn't share the audio. Share audio sound. It's actually a very exciting presentation because I already reviewed the video. And this presentation came from, or will be coming from, Dean Dieter. Mr. Dieter is the principal investigator for the VSI and CAVE laboratories at Oak Ridge National Lab. Similar to these laboratories, Mr. Dieter specializes in vehicle and powertrain research and development utilizing advanced hardware-in-the-loop practices and methodologies. Mr. Dieter is also the PI for a majority of ORNL projects that focus on vehicle and powertrain hardware-in-the-loop, as well as virtual vehicle environments. He has extensive experience in vehicle component modeling and simulation, hardware-in-the-loop testing methods, connected and automated vehicles, virtual vehicle environments, embedded controls, and sensor data emulation. So for all attendees, if you have any questions, please feel free to ask them in the chat box.
Hi, my name is Dean Dieter. I work for Oak Ridge National Laboratory. There I serve as the principal engineer for a lot of our hardware-in-the-loop activities, as well as the principal investigator for a lot of virtual physical proving ground projects, a lot of which is what I'll be talking about for this presentation. So just quickly touching on a couple statistics here. In 2018, the average human driver achieved 436,000 miles traveled between accidents nationwide. This, of course, was across the entire country, especially areas of common inclement weather, varying seasons. But what we see a lot of times, of course, in automated and autonomous vehicles is that they are often tested, of course, in states with very clear and commonly sunny conditions. So often California, Arizona, and Texas. There are, of course, some exceptions to that rule, some of the testing being done in Michigan and Pennsylvania. But most of the time, this is, of course, because this technology is still commonly being developed and is still mostly not ready for every condition that the continental U.S. throws at it. So this is some data from the state of California. This is the amount of miles traveled between a safety driver intervention on a level 3+ vehicle in California as testing is happening. Of course, we see that in general that a safety driver usually has to take over much less than that 400,000 miles that is average for a human driver. Now, granted, this is not a one-to-one comparison. A lot of times the safety driver might be taking over for a condition because it might be unsafe, not because it is unsafe. It doesn't mean that each one of these interactions is, of course, going to result in an accident. It just means that whatever the safety protocol for that end user is, they are intervening. So I put this slide up there. So what is the problem? And I'm not arrogant enough to think that myself or anybody at Oak Ridge National Laboratory has the full answer to this. But I do want to touch on, highlight a couple of the shortcomings that we have found, and at least in the area of research that we're currently performing, and that is that modeling and simulation has not caught up to the levels of requirements that is needed to have it be an end suite for simulation and development for automated or autonomous vehicles. It has come a long way. It's actually shocking and quite difficult to keep up with everything that's happening, all the companies that are currently involved. You know, there is a AV landscape that is put out by Topio, and to watch the number of companies that grow in the box for modeling and simulation is just crazy. That being said, what we've ran into for a lot of the modeling and simulation work that we've been doing, as well as the development of links between various tools, is a huge battle for proper complexity and fidelity with a huge trade-off for computational resources. And then at the end of the day, what is the focus, right? Are we trying to do a complete replication of what the real world sees or what the real world is, or are we trying to get representative control and actuation out of the vehicle for it to be comparable to what happens on road? So this is really the concept that Oak Ridge has been using to do a lot of this research and development, is what we're calling the virtual physical proving ground. It's really a combination of three very traditional development methods. Microtraffic simulation for looking at SPATs, traffic light timing, traffic control, so on and so forth. Virtual vehicle environments and virtual vehicles themselves to look at both vehicle dynamics, sensor emulation for a lot of perception sensors, controls development, so on and so forth, and then of course hardware in the loop. Actually doing validation steps and validation stages with that development in such a way that you can still have components running in real time to check things like dynamics of hard systems and of course real-time actuation requirements for controllers. So this is an overview of all the tools that we use within that virtual physical proving ground currently, with the exception, of course, of Sumo, which we will start using in 2021 as part of another project. So you can see on the top here for our microtraffic simulation tools, currently we've settled on PTV, VisSim, and Sumo as our commercial tool, and VisSim and our open source tool in Sumo. And then looking at virtual vehicle environments and sensor emulation, and doing that simulation of the various sensors of usually LiDAR, radar, camera systems, some ultrasonics, and of course varying technologies with each of those sensors. We're currently using both a mixture of commercial and open source solutions for this as well. So VTD, DSpace, and IPG, of course, being commercial solutions with entire development teams behind each one of these. And then we're also using Carla. So the reason that we are doing a mixture of both commercial and open source is for a couple reasons. Commercial tools, of course, having their own development teams behind them, we're often partnering with them and or doing collaborations with them in ways that we can really develop functionalities and features that we are needing as we build out some of these laboratories that are needing advanced functionalities, as well as looking at some of the advanced simulation packages that they're developing that we're wanting to utilize, especially when we start doing some of the work on the supercomputer. Now, speaking of the supercomputer, Oak Ridge, of course, houses currently the second fastest supercomputer. And we are leveraging that very extensively with the open source tools. So an instance is Carla. Carla, we currently are able to scale to run about 18,000 instances of Carla at a given time. We're currently working on the infrastructure to be able to do that in meaningful ways, not just spinning up different instances, but actually predefining the metric of test cases so that we can look at specific use cases for that on the supercomputer to run usually a couple 100 million miles per day if we use full utilization of the supercomputer in a 24-hour period. So just a couple quick examples of some of the use cases that we've already used for the virtual physical proving ground, and then I'll actually get into some of the nuts and bolts of what's going on behind the scenes. So we have a project with the American Center for Mobility in Michigan. We have a digital twin of their test track. As you can see, we have it integrated in both PTV VisSim and IPG. And then we're doing a co-simulation of the microtraffic simulation tool to control various traffic objects, including ego vehicles within IPG. And so what we're doing here is looking at a couple different use cases of both mergers, looking at interstate merger lanes to coordinate all the traffic objects in such a way that you don't have any type of traffic shock waves, but then also looking at speed harmonization on the interstate when you get further down the track here. So we have the merger lane, and then as we get into the straightaways, we're actually going to be forcing some fake traffic shock waves, mimicking what you would get with either a wreck or a lane shutdown, and then of course coordinating the various vehicles. These vehicles are going to be coordinated a couple different ways. They're either will be controlled if they're automated or autonomous vehicles. We're going to have 5 automated vehicles that will be able to be fully controlled by the algorithm, or human interface where the human is alerted to slow down or speed up based on the control algorithm. So to kind of give you a look of what this looks like in the speed harmonization case with the co-simulation. So here in the top you can see VisSim running the traffic simulation, and of course in the background it's also running the speed harmonization coordination for the various vehicles, and then we have the single ego vehicle in this case, but we can run up to 5 ego vehicles at the moment on the bottom running in IPG. So a Bolt is one of the vehicles that we have for use at ACM that is fully automated. And so we've partnered with Argonne. Argonne actually did the dyno testing of this vehicle to give us the full vehicle dynamics. And then from there, we have developed a full vehicle model in such a way that we can start to develop both the dynamic controller to control this vehicle as it goes through various traffic situations, but then also, of course, so that we can start looking at some of the safety messaging that's happening both vehicle to vehicle and vehicle to infrastructure with the roadside units that ACM has, as well as some of the safety constraints that happens with the radar and LiDAR units that will be attached to this vehicle. So how do we replicate the real world? At the end of the day, this is where most of my research focuses is how do we replicate the real world and how good is good enough? We know that it is some combination of the sensors that are emulated, some type of photorealism, vehicle dynamics, simulating using digital twins to get realistic environments or to do one-to-one comparisons of a real vehicle on the road versus an emulated vehicle on the road. And then, of course, ultimately to tie that back to recorded vehicle test data to do verification and validation of this work. So sensor simulation really has a full continuum, fidelity on our y-axis here and complexity on the x-axis. So this kind of goes back to what I said earlier about what is that mixture of fidelity and complexity versus computational resources. So currently we're kind of only focusing on three major sensor simulations. Idealized ground truth, where of course the program itself, the virtual vehicle environment or the sensor emulation software knows that a person is a person and a car is a car because it's part of the simulation. We can generate object lists and have idealized sensors in that case. Phenomenological is essentially a probabilistic or a statistical model, except for it uses some of the things like geometry or material to inform that statistical model to have a little better accuracy. It also allows us to generate statistical noise into the sensor model if we need to be looking at ways to handle the type of noise that we traditionally see from radars especially. And then physical modeling, where you're using a method like ray tracing that was developed by NVIDIA to emulate the IR lasers from a LiDAR or the radio waves sent out of a radar in such a way that it is trying to emulate the physical characteristics of that as it goes out, hits a certain geometry, hits a certain material with different reflectivities, and then of course emulates the reflection of those various entities back into the sensor itself. So again, if you're very familiar with a lot of the simulation software, this is probably something that you've seen quite a bit. So this is actually a platooning project that we're currently working on, where we're using idealized sensors to do both the road markings to find the free space for drivable area. You can see the broken up green blocks. Those are representing LiDARs and representing the angles for which the LiDAR hits, and the yellow box around it is an idealized radar sensor. Moving into the phenomenological sensors that I mentioned earlier, you could see the statistical noise here that is thrown in on top of the other hitboxes and other detections that are happening. Of course, the distance of the object and the size of the object is also having effects on how well that signal is coming back, and you can see that by the bars across and on top of the various vehicles as well as the guardrails. And then full physics space modeling, where we are modeling the various lasers as they go out, hitting different objects with different reflectivities. You'll actually see that the windows can be seen on the top there. You know, a big portion of this that I really want to highlight is we really want to focus on not only simulation packages and models that can be emulated in such ways that are very realistic, but really the real-time component is also very important. Ultimately, a lot of the work that we do ends up into one of our hardware-in-the-loop or vehicle-in-the-loop laboratories, and so the capability to run these real-time is very important to us, and so we get that out of the packages that we're currently using. At the end of the day, though, for a perception system, the environment's everything. So this is a quick example just to show, at the end of the day, how hard it is to do a true replication of a real environment in a simulated platform. So on the left there is some real data And you can see that at the end of the day, we have undulations in the road. And so we don't have the perfect concentric circles that we have in the simulation package, where the road is a really nice flat surface. How much of an impact does that actually have at the end of the day on actual actuation and detection and control? You know, that's something we've not dug deep enough into to find out. At this point, we're still trying to determine metrics for how well you measure simulated environments versus the real environments that they're mirroring. Things like contrast or saturation of color. What is its impact on object detection or free space detection? How well do simulated vehicles and people correlate for trained networks? These are all things that are very important to figure out as well. This is something that is, of course, very difficult to do, mainly from the perspective of not every network is trained the same way with the same set of data. And so the differences in the training data sets can have huge impacts based on things like contrast, sharpness, saturation, color temperature, things like that as well. And so we really want to start looking at which one of these variables in object detection has the greatest impact when we're trying to replicate these things in modeling and simulation. And then lastly, photorealism. Does photorealism matter? What is the impact? How large is the impact? Ultimately, does it have enough impact that it makes it more or less useful tool for development? Is very important to consider and look at. So digital twins, of course, are very important if you're going to do any type of verification or validation work. You have to be operating a real vehicle in the same environment that you're operating a simulated vehicle. And really, at least for us, we've gone down the path of 3 different options for creating these digital replicas of the road. One being manual recreation. We're currently using a tool called Roadrunner that was originally owned by Vector Zero, but it's been bought out by MathWorks. At the end of the day, we take GIS data and satellite imagery, and we redraw the roads. And then we can actually take LiDAR point cloud data from our test vehicle and overlay that on top of that to get even more detail. We're doing a pilot program with Understand AI. It's a subsidiary of DSpace, where we record data on our test vehicle, and then a AI-based algorithm actually generates the road for us. Unfortunately, it does involve some post-processing, but the fact that a human doesn't have to sit down and do 100% of the generation is a huge time saver. And so we're also looking into this option. And then, of course, lastly is a mapping service, where highly instrumented vehicles take surveying level equipment and do scans of full road networks, and then ultimately they do the post-processing and deliver a finished product. You know, why is this important other than what I've already mentioned with trying to do replications of a real vehicle going down the road, and of course the simulated vehicle going down the road, and looking at sensors and perception and things like that? Well, it's also very important for things like LiDAR localization and development of your perception stack. So in our case, we use ROS and AutoWare. So what you're seeing on the left is the Carla simulated environment, and then we have an HD map of this simulated environment on the right running in AutoWare. And rather than using the GPS localization, we're currently using LiDAR localization to find ourselves within the HD map. Of course, we all know this is a really important functionality for level 3+ vehicles. So as I had mentioned before, often we are taking a lot of what is being developed in our co-simulation or in our virtual vehicle environment simulation, these digital twins, so on and so forth, and bringing that back into hardware-in-the-loop environments. This is one of our new laboratories, the Connected Automated Vehicle Laboratory, or the CAVE Lab as we're calling it. It's a really unique facility. The dynamometers are actually completely steerable. Currently, they're on ultra low friction ball casters so that you can have full steering capability. In the future, we actually have steering force reaction generators that are going to be developed for this system to also give proper torque feedback and feel into the steering rack for either a human driver, or also we've ran into a couple issues where you need that feedback into a vehicle system to get a check engine light or traction control to kick in. We use this D-Space rack on the far right to do full emulation of sensors. And so going to the next slide. This here is another picture of the system. So we have purchased one of these ESI systems from D-Space, and ultimately what it does is it formats the LiDARs, the radar, the camera from the virtual environments in a message format or in a data stream format that matches the actual sensors from our test mule vehicle. So that vehicle you saw earlier is completely different now. It's actually outfitted with 4 different radars, 4 different LiDAR systems, and then also a slew of cameras. So that is what we're taking out to the roads to do a lot of our data collection on our digital twin roadways, and ultimately using the system to do the replication of what that sees in a simulated environment to do that validation and verification work. So last slide here. This is really just an overview of the various systems. You know, I had mentioned before that a lot of this is broken down into work on digital twins, perception, some work on photorealism, and then of course vehicle dynamics. And just really one of the key things that I wanted to touch on here is there's a lot of talk for automated vehicles and autonomous vehicles, but ultimately level 2 vehicles still have a lot of areas that they can make huge impacts on both safety and energy efficiency. Things like HMI and other cues to the driver, as well as some minimal control of the vehicle, still has a great opportunity to have these type of impacts, and that's why we've included this visualization suite as well, so that the driver can interact with the virtual environments. And that ends my presentation. Thank you very much for your time, and I will take any questions that you have.
So Zirin, I guess I'll start with, can you hear me okay?
Yeah, Dean.
Perfect.
Very clear.
All right, so
I can reiterate. Sorry, I can reiterate those questions, although you have seen them, but just for information for all the attendees. First question came from Ethan. I think he was asking about the digital twin, and I have this same question as well. The way that you interpret or you comprehend this term of digital twin, is it the similar way as like LG Guo Dong, he just explained, as a virtual simulation of what is happening in the real world, or something beyond that, more complicated kind of thing?
I think this is a really difficult topic because it really depends on what are you trying to look at? What is the focus of the project? A digital twin for some of my transportation colleagues that are looking to manipulate traffic flow is very different than a digital twin that I need if I'm looking at perception and the final control and actuation of the vehicle based on what it sees through the perception stack. So, I think digital twin is one of those terms it's really kind of thrown around a whole lot, but it has a pretty broad range for what it can represent. For the case of this project, we are focused on energy efficiency, and we're also focused on control, especially looking at latencies of the communication, the actuation of the vehicle, so on and so forth, because at the end of the day, it's a cooperative coordination algorithm. And those differences in the actuation has an effect further down the line as we do control of a couple hundred both physical and virtual traffic objects. So for us, it's making sure that the roadway is represented properly in the markings, the size, the distances are appropriate, objects are along the road are fully represented so that they're picked up by both the radar and LiDAR systems that are being emulated. That's kind of the focus and why we have that digital twin for that project is really to make sure that we can do a one-to-one comparison, because this project was a model validation project. It is trying to figure out what kind of agreement we get between what we did in modeling and simulation and hardware in the loop with the controllers versus what we actually get when we put it out on the track.
Mm-hmm. I see. Thank you. Thank you for this. Another one, I think I can simply combine the question coming from Guoyuan and Chris. So you have been talking about different simulation tools, modeling tools. And I mean, what is the potential insight for the synchronization of those different kind of platforms? And how would you compare open source to commercial tools today? Are there any clear advantages to one over the other?
Yeah, so we do find that most of the commercial tools we use, a lot of the perception sensors are definitely have an extra layer to them for development. And, a lot of this makes sense. There's very real research dollars being pumped into a lot of the commercial solutions. And there's usually greater flexibility in those tools to get things set up quickly. That being said, the open source tools are extremely flexible, whereas the commercial tools often lack a lot of that flexibility. And so I had mentioned some of the work that we're doing with our supercomputer on site. It's really to the point now where we use the open source tools solely if we're going to do any type of scalability, because of the flexibility we gain from the open source tools. We can actually manipulate the code enough to get it to run on a platform like our supercomputer. That is something that we have tried to explore with some of the commercial solutions. And it just ends up being, if there's not a business case for them to actually put the research behind it to get it to scaled, it just doesn't happen. And so open source tools, and the gentleman that presented from LG touched on this a lot. The flexibility is there for advanced research, whereas I think a lot of the commercial tools are still beneficial for certain types of research, but a lot of times they are more geared towards the full development of an applicable control scheme.
Thank you. Appreciate that. For other people, if you have any question for Dean, please feel free to ask in the chat. Thank you once again, Dean, for setting up that in Garage.
Oh, no problem. Thankfully, I only got interrupted once during the presentation by one of my kiddos. I do want to touch on one more thing that I forgot to leave out. Sure. A lot of people ask us why we kind of did this approach with trying to combine hardware in the loop, virtual vehicle environments, virtual vehicles, and then the micro traffic simulation. And a lot of this comes down to the fact that, as a national laboratory, we have both government-funded research, but we also semi-work as contractors, and we're often working with suppliers, tier ones, and OEMs. Well, we cannot settle on a tool chain because often our partners have their own tool chain. And so we end up having to switch tool chains quite a bit. And that's really what brought us to build links between a lot of different software packages and adopt different methodologies to kind of have at least a semi-standard approach to link these all together. And so synchronization is kind of the bane of my existence as far as a lot of that comes down to, because things like vehicle systems always have to be able to actuate full real time. But you get into these areas of soft real time where you need something to actuate very close to real time, but you don't actually need it as a full requirement because there's no physical piece of hardware that needs that very discrete time step. And so very much we try to separate all the hard vehicle systems on some type of hardware in the loop box to make sure that they can achieve that real-time time step. And then all those soft systems we often keep on a whole nother either PC or set of controllers so that we can do this pseudo real time. And then we have a handful of scripts as well as some control that we have running in the background that resolves that soft real time to connect to the real time.
Got it. Thank you. Thank you very much for your explanation. Thank you once again, Dean. Okay. If there's no more questions, let's go to the next presentation. Xuanpeng, would you mind sharing your screen right now? So our next presenter is Xuanpeng Zhao. Mr. Zhao is currently a PhD student in electrical and computer engineering at the University of California, Riverside, advised by Dr. Guoyuan Wu and Dr. Matthew Barth. His research is focused on computer vision, embedded system, autonomous vehicle, and robotics. He is currently involved in the Digital Twin project sponsored by Toyota Infotech Labs in Silicon Valley. So Xuanpeng, you can take over.
Hello, everyone. I assume you can hear me. And
we can hear you. The screen is gone. The screen that you were just sharing is gone.
Hold on a second. Can you see the screen now?
Yes.
Okay. Did you see as a full screen or?
It's not the full screen. It's slide by slide.
Hold on a second.
Okay, maybe you can swap your presentation. And by the way, thank you everyone for staying. I know some of you especially East Asia, like China, Japan, Korea, it's midnight already. But we still have 4 more very exciting presentations. So hopefully you can, enjoy those presentations and get more results from those. Go ahead, Xuanpeng. We can see the full screen.
Okay. Thank you. Hello, everyone. My name is Xuanpeng Zhao, and I'm currently a first-year PhD student and at UC Riverside. Today, I'm going to present the development of Sumo and Unity integrated platform. Firstly, I will explain the motivation, why we built this platform, and then we will introduce some backgrounds. In the third part, I will introduce how we built the integrated platform. Then we use the case study to show how the platform works. Finally, we will have some discussion. Currently, transportation system and emerging technologies aim to improve safety, mobility, and reduce congestion, energy consumption. Many researchers have developed a lot of methods to solve the problem. To test them in a lab-controllable environment, variant simulators have been developed. As new technology developing, although some tools are expert on their field, they are not capable of researchers that need multiple aspects. So it's a right time to have an advanced or comprehensive modeling platform to quantify the system-level impacts of these new technologies. Many researchers noticed this gap and developed several advanced modeling platforms. Here I'm going to introduce 3 of them. Firstly, the University of Michigan's MCT lab is used here in concern with Vism. It's a highly developed testing facility that combines the fidelity of real-world testing with the immersive connectivity of a CAV simulation environment. As you can see from the figure 1, the left part is Vism and the top right part is in the real world. The next is the Kala. Kala has developed a co-simulation feature with Sumo, like Dr. Feng presented. This allows to distribute the task at will and exploit the capabilities of each simulation in favor of the user. In figure 2, the left is Kala and the right is Sumo. The last one is Ventos, developed by UC Davis. As you can see from the figure, it combines Sumo and Omnet++. It can be used for studying vehicular traffic flows collaborative driving and interactions between vehicle and infrastructure through DSRC-enabled wireless communication. And there are more advanced platforms, just like Dean presented, integrate several multiple simulators together. Thank you for your presentation. And for the next slide, I'm going to briefly introduce the Sumo and Unity. For Sumo, a microscopic traffic simulator, it can create a realistic traffic flow, and its traffic light system, car following models, and lane changing models are very useful for traffic-related research. And Unity is a 3D game engine-based simulator. For traffic-related research, it can provide a 3D realistic visualization and various sensors, such as a LiDAR and a camera, which means it can test visual-based algorithm. And of course, not only us notice the gap here. There are several researchers who have developed a connection between Sumo and Unity. They are all involved the user-controlled vehicle in the simulator. But there is a major drawback of this connection. They developed this only in order to satisfy the need for a realistic visualization of traffic. They didn't fully exploit the advantages of the game engine. Well, if you look closely to the figure on the bottom, you can find there's a red circle which represents the position of the user-controlled vehicle. This means they didn't project the user-controlled vehicle into Sumo, so the vehicle in Sumo cannot react to the user-controlled vehicle. Furthermore, in our integrated platform, we have CAVs controlled by Unity that can react to the legacy vehicle controlled by Sumo, and those legacy vehicles can also react to our CAVs. This feature provides the possibility to evaluate algorithm in a mixed traffic scenario. Here is our system architecture. Let's begin with the traffic stream generator, which is on the bottom right. This generator can give us a traffic list, which indicate the vehicle's name, departure time, and other configurations. Once the traffic list is generated, Sumo will load the vehicles based on the list. We call Sumo control vehicles a selective vehicle, and they are controlled by Sumo default car following model and the lane changing model. In every time step, Sumo will send the vehicle information to Unity via UDP communication. The information distributor in Unity will identify if this is a new vehicle ID or existing ID. If this is a new ID, Unity will generate a game object with this ID. Then you will go to vehicle control type classifier, which is a random number generator that follows a uniform distribution. When the random number is larger than the threshold, we set it as a selective vehicle. Otherwise, the vehicle will be a CAV. CAVs will be controlled by user-defined control algorithm. For user-controlled vehicle, we will identify it by its special vehicle ID. And let's go back to the information distributor. If the vehicle ID is an existing ID and is a legacy vehicle, then we will update its position, velocity, heading, etc. Okay, when the vehicle information is sent back to Sumo, it goes to an information distributor in Sumo. Then we will update the information of CAVs and the user control vehicles in Sumo. In both sides, we have a vehicle terminator. Its main job is to delete an inconsistent vehicle between existing vehicle and the vehicle transmitted from the other side based on the vehicle ID. Here is our hardware setup for human in the loop. As you can see, we have 3 main screens to ensure the wide angle of vision, and we have cockpit, steering wheel and the brake panel, gas panel for human drivers. Here is our case study. How to merge on to highway without crashing is a common problem in our daily life. Hence, we choose ramp merging scenario as our case study. We defined our user-controlled algorithm to provide a recommended speed for human driver to follow, so we can evaluate the performance of the algorithm. Here, we use a game theory merging strategy to control the CAVs in Unity. The basic idea of this strategy is to determine the merging sequence for conflicting vehicles. With the information of conflicting vehicles, such as acceleration, speed, and position, we can compute the cost for those vehicles and perform the action with the lowest cost. We use a real-world network, which is Columbia Avenue, as our simulation network. There are 2 main lanes and 1 ramp lane to form the ramp merging scenario. We firstly build the Unity network based on the Columbia Avenue, then build the Sumo network based on the Unity network. We also set a bunch of waypoints in the Unity network to make sure the movement of CAVs. Here is our test scenario configuration. We set the human-driven vehicle as a ramp vehicle. There are 2 types of human-driven vehicle. One is a legacy vehicle, which means there's no connectivity and no sensors. Another one is connected vehicle with head-up display, which can give a recommended speed for human drivers. We set the 2 main lanes have 2,400 vehicles per hour, and the ramp has 1,200 vehicles per hour. And we focus on 2 cases. One is legacy vehicle with 0 penetration rate. The second one is that connected vehicle with 100% penetration rate. CAVs are equipped with LiDAR and controlled by game theory algorithm. Human-driven vehicle has 3 mirrors that just like in the real world. Here is our demo video. Let's start it. As you can see, the red vehicle in Unity are corresponding to the red vehicle in Sumo. Same for the white vehicle. The red vehicle represents the CAVs, and the white vehicle represents the legacy vehicle. And you can see there is a blue vehicle on the ramp. The blue vehicle is our human-driven vehicle, and we're gonna show the first-person perspective of the vehicle in the next video. As you can see, the platform provides a realistic driving experience. The average FPS can reach 30, and the latency is around 30 milliseconds. Here is our partial preliminary result of 2 cases. One typical pro of this human-in-the-loop simulator is to see how the head-up display can affect the driver behavior. As you can see, comparing the velocity of 2 cases, the driver tends to drive smoother. And according to the minimum headway, the driver with head-up display tends to keep a large gap between the preceding vehicle. Another pro of the human-in-the-loop is we can compare and evaluate the driver behavior between different drivers. Here, we invite 3 drivers to do the test on the case 2, which means the driver has the head-up display. As you can see, different driver has totally different driving behavior. The most aggressive driver didn't follow the reference speed at all. Here are some conclusions. The conclusions are very intuitive. First is the driver who follows the head-up display record speed can have a larger gap between the preceding vehicle, and the different driver have totally different driver behavior. And also, there are some challenges when we develop the platform. When we have a higher volume traffic, then the latency will increase. We list several potential solutions here. First one is optimize information transmission method. For right now, we are transmit with string, but like for future, we can use some like JSON file to optimize the transmission method. And the second, we can display the nearby vehicles only, which can reduce the information transmission needed. And the third one is we can transmit information every like 10 time steps. It can also reduce the information demands in the communication. In the next slide, we also provide an incomplete version of integration of Sumo and LGSVL, since the LGSVL is also a Unity-based simulator. And that's all. Thank you. Any questions?
Thank you, Shenpeng, for the presentation. One question I have for you might be, you presented the background in the first few slides regarding what UMich has done, what others has done. What do you think is the key contribution or the key difference between your work with respect to the other state of the art?
Yes. Let me go back to the slide. Yes, for here, I think the major contribution we have is that in the Unity, we at the Unity controlled vehicles such as like several presenters mentioned before, like Apollo or AutoWare. But in our cases, we can define our CVs by our algorithm, and the CVs in the Unity can react to the background traffic controlled by Sumo, and the Sumo vehicle can also react to the CVs controlled by Unities. I think it's the major contribution in this integrated platform.
And followed by that, I guess the question coming from Chris is for you, or maybe the others, but anyway, can you, no, there's another question, sorry. The question coming from Matthew Watt is that how do you handle the mismatch of position between Sumo and Unity? Because based on his experience, is that Sumo is quite bad at lateral dimension, and he can imagine that you have more details in Unity for lateral position. How do you handle the mismatch?
Yes.
Go ahead.
Yes, for the lateral position, we we directly transmit the vehicle into the position in from the Sumo, and get from the Sumo. So I'm not sure the lateral position problem. Could you like elaborate it a little bit?
Yeah, maybe you guys can talk in the chat box.
Okay.
One last thing, as I mentioned earlier, can you implement widely different behavior models in Sumo, or is the traffic fairly homogeneous? Like the traffic model in Sumo, is it like the default model, or can you implement some other models in that?
Well, there are several models can be chosen in Sumo.
Okay.
Yeah.
So, multiple options, right?
Right.
Okay. Yeah. Thank you again, Shenpeng, for presentation.
Oh, I see the problem. I see the question.
He's typing
So
that. He's typing
yeah. Okay, I can talk in the chat box.
Yeah,
okay,
thank you. Josh, are you online? Josh, because
yes, just working on unmuting myself there.
Yeah, thank you. I think our next presenter, Pin, she has some problem on setting up. Maybe you guys can swap. Can you present earlier, right now?
Yeah, that's well. Let me try.
Thank you for flexibility. So while he's setting up, I will do the intro. Our next presenter, Joshua Old. Dr. Old is a technical manager in the Transportation Research Systems Modeling and Control Group, Energy Systems Division, Argonne National Lab in the United States. He completed his master's degree in 2007 and his doctorate degree in 2011 in the Civil and Materials Engineering Department at the University of Illinois at Chicago, with the concentration in transportation. He also completed a postdoctoral appointment with the University of Illinois at Chicago and Oregon's Transportation Research and Analysis Computing Center in 2014. Dr. Old has experience in a variety of areas in transportation, with a primary focus on dynamic activity-based travel demand microsimulation models and the interactions between travel demand and intelligent transportation systems operations. So Josh, if you set it up, you can go ahead.
All right, thank you. Is it displaying correctly?
Not yet. Have you shared your screen already?
Let me try again.
Coming right now. Yes,
Coming
right
through.
now. Yes.
Okay.
Yep.
And let's get it into slide mode. Switch. Okay, how does that look?
Perfect. Full screen. Perfect.
All right, thank you for the introduction. I will be presenting today on some work myself, my colleagues at Argonne in the Vehicle Mobility Systems Group, and other colleagues across the National Lab Complex as part of the U.S. Department of Energy Smart Mobility Consortium have done on modeling the impacts of various future mobility technologies using a modeling workflow we have developed around our Polaris agent-based simulation tool. So in terms of background, we are all aware that the transportation system is being heavily disrupted, the focus today being largely on connectivity and automation, but a number of other technologies like electrification, e-commerce, and so on are also concurrently changing the way transportation system operates. And the key insight here and what really motivated a lot of the work around the Smart Mobility Consortium was understanding the interrelation between these changes. So changes in connectivity or changes in vehicle automation technologies don't just affect how those vehicles operate, but they also affect how people travel, how people operate in those vehicles, how they move through the system, and so on. So we really wanted to put together a workflow to explore the various scenarios considering all of these issues, or at least as many as we can get into our different simulation models. And this has been done through the development of a comprehensive modeling workflow to address a lot of these complex questions around interrelationships between different technologies and different behaviors in transportation systems. So this is a workflow, again, that has been developed by the Smart Mobility Consortium with the instance here really focused around the Polaris agent-based transportation system model. So that really controls how travelers behave, how the transportation system on a regional scale is controlled, how goods move, and so on. But that has a lot of complex interactions with other models that we have integrated into this workflow, including looking at things like EV charging, land use changes through land use modeling, vehicle markets through market modeling, and then connections to microscopic traffic flow and multi-vehicle control. So a lot of the things that have been discussed in earlier presentations in this session, really how these, let's say connectivity or automation technologies on individual vehicle and groups of vehicles, how that changes both microscopic traffic flow and then how that can flow into things like more system level modeling that's been being done through Polaris. And this workflow then is being used to generate a large number of metrics, including vehicle energy consumption, mobility characteristics, metrics that have been developed to combine these measures, for example, the mobility energy productivity metric and so on, to characterize changes to the traffic system, that transportation system that different technologies would have. So what we really think our workflow centered around Polaris is unique for a number of reasons, including that it's one of the few workflows that actually contains a full-featured activity-based model. So this is really, and I'll go into more detail in future slides, looking at how individuals travel and the decisions they make that cause those travels to arise. It also includes freight movements and freight shipments, vehicle energy consumption, and integrates all of these, both the modeling of the demand, the network assignment, and traffic flow into one computationally efficient framework. Again, this is fully agent-based. We do connect with external optimizations to represent a lot of these technologies, things like fleet management, vehicle sharing, and so on, done through our external optimizers, all in a high-performance code base. So it's really enabling us to run large-scale models. So we can look at the example I'll show today is a model with about 10 million agents moving in a 20-county area around Chicago, Illinois. At 100% sampling, so we can really get to a lot of detail about the complex interactions with these agents and their vehicles, whether it's a transit vehicle or a rideshare vehicle and so on. So just a quick background on the development and updating of this model. So Polaris, again, is sitting at the center of the workflow, is really an activity-based model that tries to account for choice-making and actions that all travelers in a transportation system would make, from long-term choices like where they live, work, and which vehicles they own, to day-to-day choices, including what type of activities they want to engage in on sort of an average travel day, how those activities will be planned in terms of the mode choices and destination choices that they're traveling to, how they would be scheduled both within the agent and within other household members or other agents within the system. And then a lot of detail about the actions they take around things like which routes to choose, so which streets is the vehicle going to drive down, and then how does the vehicle interact with other vehicles in the traffic stream. So that's the base model, but this has been heavily enhanced to represent different, to be able to account for different future mobility options, largely around connectivity, automation choices, new mobility options, things like rideshare systems, vehicle share systems, and so on. So we've had to update these models, including looking at things like technology choice. So on a personal level or a household level, which technologies do people own? How those different technologies influence the choices that they make, looking at how, for example, changes in value of travel time would occur and would change the daily activities that people engage in. But we also look at more system level things. So how do TNC, or as those vehicles become automated SAV operators, understand the system and position their vehicles and move their vehicles under these different technologies? How does multimodal dynamic traffic assignment influence the model and transit simulation? So really looking at outside of not just one trip, but people potentially taking a taxi to a transit vehicle and then getting off that vehicle to an e-scooter or other micromobility option. So looking at all of these movements through the system. And then incorporating a lot of the ACC, CACC, AV impacts, and again, things that the previous presentations have looked at. So abstracting from the detail on the micro level up to the meso scale to understand how traffic flow changes at different penetration rates of these technologies. So linking this all together through our workflow has really enabled us to look at some of these future mobility scenarios. A little more detail on what we've done specifically around CAV or TNC modeling. So we do have, as I mentioned, the AV traffic flow model, which really tries to parameterize changes in fundamental traffic flow diagrams based on different penetrations of technologies. So implementing this into our mesoscale traffic simulator within Polaris, depending on whether people do or do not own vehicles with different connectivity or automation capabilities. We've also updated and updated, our TNC and SAV simulator, which is, again, this fleet modeling, both on where vehicles are located, how they move, how they reposition to, or how the operator makes ride matching, optimal ride matching between individuals requesting rides, how those vehicles reposition, and then how they route and pool to optimally provide mobility through that system. So this simulation has been implemented. We've also implemented a version of this, but for privately owned AVs. So it's more of an optimal decision making, but on a household level. So how can a vehicle that is able to reposition itself be shared amongst multiple household members to accomplish more in a day with fewer private vehicles? So that is the baseline model that we've been testing. We have done extensive validation on this model to ensure both that it's representative of the system we're trying to model. For example, in the Chicago area, some validation work here showing travel to trip distance distributions and mode share distributions by different area types, and we can see we're matching quite closely data we're collecting from our local planning agency. That's both on the individual travel behavior level. This is more on a system level, so we can see the vehicles in motion by time of day, as mentioned, very close to our baseline, as well as detailed link level counts. So that on the right, we can see diurnal counts coming out of our model in terms of traffic flows by hour of day, compared to loop detectors throughout there's about 800 loop detectors throughout the Chicago highway system. And we see we've matched the diurnal distribution of vehicle movements quite closely in this regard. We've also done a set of backcast validations. So this is to ensure that the model is not only representative and accurate for our baseline scenarios, but also to ensure that it is sensitive and suitable for forecasting purposes. So this is basically taking our baseline model and then backcasting in Chicago to try to capture the effect that the introduction of TNC and expansion of TNC throughout the Chicago area have had on overall traffic. And the results here show we are able to capture the trends in transit where there's been a slight reduction, and taxi and TNC movements where there's been a massive increase since 2014 to 2018. So we validated that our model is able to capture these changes. So as the TNC fleet expands and operates in different areas with different pricing structures, we are able to show that the right number of people are moving in through that system. So that was the development and validation of our Polaris workflow. Now, as a consortium, the Smart Mobility Group has developed a number of future mobility scenarios. So the initial set of 3 scenarios that we looked at in the last round of the Smart Mobility work are defined as thusly. So we have one scenario which is more of is basically an extension of current day trends. So we have basically current day TNC or rideshare usage, but expanded a bit. So we have a much higher percentage of people actually using these rideshare and ride pool systems, more likelihood of individuals pooling, and some partial automation making its way into the private vehicle fleet. And then we have, so that's more of a near-term scenario, and then we have 2 more long-term scenarios, one which is where automation is increased drastically, so there are many autonomously operating vehicles. In the first scenario, we have a high sharing, so the autonomous vehicles are largely confined to shared vehicle fleets. And a second scenario where we have low sharing, where the automated vehicles are almost exclusively, there's some fleet, but they're mostly privately owned. And we really want to look, let's run these scenarios through the workflow we developed and see what would be the outcome in terms of the metrics that are of interest to our model and process. So at a very high level, if we compare the 2 long-range scenarios, we see that the shared fleet system do enable much higher system efficiency in terms of mobility and congestion and energy use compared to privately owned scenarios. So if vehicles are privately owned, so largely within families, although there is, again, some expansion of an SAV system, but most vehicles that are automated are owned privately, we see about a 22% increase in energy use, 25% increase in total miles traveled, leading to an 18% reduction in speed. So it drastically increased congestion throughout the model region, again, Chicago area in this case. Although there is a 7% increase in personal mobility, so people are able to travel a bit more due to the reduction in travel time cost in the automated vehicle, but overall, the transportation system performs significantly poorer. And this is compared against the a scenario where vehicles are largely shared, so the automated vehicles are operating in SAV fleets. In this case, we see an 18% reduction in VMT and a 17% increase in speed. So basically drastically decreased congestion from the baseline scenario at no cost to personal mobility. So even though people are disposing of more vehicles and using this fleet more, they're still able to travel the same amount of productive miles. And overall, we have a 23% reduction in energy, so significantly more efficient than the privately owned vehicle case. And these results are largely observed due to what we see as the operational differences between SAV and privately owned AV. So in the high sharing case, only about 4% of vehicles of miles travel are unloaded throughout the day. So the vehicles due to the high utilization from so many people, so drastically expanded fleet, being able to service a lot more people, the vehicles tend to stay more loaded during the day, whereas privately owned vehicles spend a lot of the day unloaded. So about 15% of total miles traveled in the system, where vehicles are largely privately owned, are spent being empty. So basically repositioning between household members. So if one person takes the vehicle to work, then the vehicle can drive itself back home to pick up the next household member and so on. So the vehicle repositioning between rides is a lot less efficient when it can only reposition between the members of one household. And this has the effect of reducing average vehicle occupancy from 1.5 down to about 1.2 when so many people have private AVs. In terms of the ride-hail operations, we see that increasing both the size of the ride-hail fleet and automating that fleet to enable more efficient repositioning do enhance the use of ride pooling. So about 27% of miles become ride pooled from 22%. And we only increase deadheading miles, that's the repositioning miles, for the shared vehicle fleets to 14% from 13%. So we actually increasing the average TNC occupancy, so over 1.08 from the baseline of 1.04. But these changes aren't only driven by how the shared vehicle fleets operate, it's also driven by individual traveler decision making. So we do see that as more shared and more autonomous vehicles make their way into the system, and households dispose of vehicles accordingly to make use of those systems, that we also see transit use grow. So people that are comfortable disposing of a household vehicle because of the existence of ubiquitous shared vehicle fleet also tend to make more transit trips, largely in the areas that are already served well by transit. So while not directly controlling that, we do see an increase in transit growth. Whereas in the opposite sense, the private AV ownership encourages additional shared vehicle trips. So even though we have more people disposing of vehicles, let's say in the private AV scenario, we still have about the same ratio of SOV trips as we do in the baseline. And then another interesting finding here, and I have a visualization of this on a later slide, is that urban households tend to shift to transit while suburban households tend to shift to TNC when disposing of a vehicle. So that's the vehicles that they choose, but they also use those vehicles fundamentally differently when a household owns an AV versus when it doesn't. So these results here are limited to the case. This is comparison within the high private AV ownership scenario. When we compare households in that scenario that have an AV with households that don't, we see that ownership of an AV increases overall driving for that household by about 82%. So some of that is due to the vehicle repositioning, especially in the PM peak when it's moving between household members. But a lot of that is also due to more longer discretionary trips. So people being able to make productive use of their time in the vehicle and not having to deal with the stress of driving, it decreases the travel time cost for those trips. So people tend to make longer trips. So we don't have the work and school relocation necessarily reflected in this model. Because we don't have the long-term land use choices here. But we do see for the discretionary trips, people tend to take about 3 to 6 miles longer, so adding about 30% extra miles onto the trips they make. And this is to get to more optimal opportunities because they care less about the cost of reaching there. So we do see these households, let's see, per capita miles traveled in households that have AVs is about 36 per day versus 20 per day for households that don't. So this 82% increase in VMT, interestingly, has been at least similar observations in field studies that have been done. So there was a study in University of California, Berkeley, trying to basically replicate households that would own an AV by providing cost-free shuttles or cost-free chauffeurs. And in those households, and it was a small-scale study, but they did see about an 85% increase in total miles traveled just from people sending the vehicle to go do errands and pick up kids and so on. So interesting that we have some, at least field verification of this behavioral shift that we expect to see. As I mentioned in an earlier slide, one of the other findings, or key findings, when we were running the long-term scenarios with more shared vehicles is that the transit and TNC operations, instead of being perfectly opposed as many times assumed, they can be complementary, especially as households dispose of vehicles to make more use of the shared vehicle fleet. In many cases, especially where transit is already high quality, the transit mode is competitive in that case, and the households just switch to transit instead of switching only to the TNC. So we can see the change in mode share in terms of people choosing transit or the shared vehicles is almost a mirror image of each other. So transit grows in downtown, even in the high vehicle sharing scenarios, and TNC grows mostly in the suburbs where there wouldn't be really transit to deflect to. So overall scenario results are compared here, and this is both cases where, again, we have the demand scenarios where there's high sharing and automation, and high automation and low sharing. And we also compare that for scenarios of vehicle technology change. So we have a business as usual growth in vehicle technologies, things like new powertrains and engine components and so on. And then a VTO, Department of Energy VTO success case where we have more advanced vehicle technologies, including more advanced and efficient automation. And we can see the impact that each of these scenarios has in terms of the total miles traveled, productive miles traveled, which generally stays approximately the same across scenarios, and then average speed, which is the proxy for congestion in the system. So overall, we see that basically the high sharing scenarios have about the same level of travel, but it tends to be more efficient and more energy efficient versus the private AV scenarios. So just to wrap up with some key findings, we find that in the high sharing, but more current day technologies, we have about a 12% reduction in VMT and energy if people dispose of household vehicles and switch to shared fleet systems. If those shared fleet vehicles happen to be automated, we can have an up to 3% reduction in VMT and energy, whereas if those automated vehicles are not in shared fleets but are in private fleets, we have about a 22% increase in energy, so it's basically flipped from the previous scenario. And this is driven largely by changes in travel behavior, both from sending vehicles back and forth and from the 82% more vehicle miles traveled within households that own AVs. In all these cases, however, transit use tends to increase whenever there is a high sharing and increased shared fleet scenarios. So transit does serve an important purpose in backstopping some of this, mitigating some of this congestion increases that could occur with privately owned automated vehicles. So with that, I will say thank you for listening and acknowledge the work, so the support of the U.S. Department of Energy Smart Mobility and EEMS modeling teams, and as well as the working contributions from Argonne and partners across the lab complex, and take any questions. Thank you.
Thank you. Thank you one more time, Josh, for flexibility to swap your presentation order. I think two questions coming from Jachi. And he was asking, will the ownership of AV and sharing of AV interacting with each other? Because he has been wondering if this has been considered, and can this project of Polaris go down to the level of activities and vehicle ownership choices?
Yes, it explicitly does. So we definitely model down to the level of activities and even how those activities change when there are different types of vehicles available. So if a household has vehicles they can share or doesn't have vehicles and is forced into transit, all of these factors, let's say, figure into the travel outcomes that we model. It does have a AV ownership and a household disposal model. So households can choose to dispose of vehicles based on the quality and level of service of shared fleets and transits which may be in the area, or they can choose to purchase AVs depending on the costs in the scenario we set and the individual household needs and travel behavior. So all of these things and scenarios around that are definitely a part of the ongoing work under smart mobility and can be considered both in the Polaris and in the wider workflow, which also connects to some of the vehicle market modeling work that is done across the lab complex as well.
Mm-hmm. Thank you. And he has a more specific question in the chat box. Maybe you can discuss it with him in the chat. One general question I have actually is, have you considered, especially for the current situation, the impact of like pandemic, like COVID, will have any like influence or impact on the ride-sharing choices of people in the future?
It does. It definitely does. That is ongoing work, so I can't say much about it at this time. But there is work, let's say, that has been done by some of the universities we're partnering with on collecting data about how, let's say, risk perception and mode choices around both transit vehicles and ride-sharing vehicles are changing. So there's panel surveys, one for the Chicago area and one for the US as a whole that have been looking specifically at this topics, and the idea is to get that into the modeling scenarios that we are doing as well. But
Thank you.
At a takeaway, yes, it has a very strong impact in terms of the ability, willingness of people to share rides.
Sure. Thank you. Looking forward to that in the future. Thank you very much again for your presentation, Josh. So our next presenter will be Ping Wang. Ping, if you can share your screen, start. And yeah, I will do the intro. Dr. Wang is a researcher at California Path, UC Berkeley. She's mainly working on deep learning-based automated driving projects on the Berkeley Deep Drive Consortium and vehicle platform developments. Prior to joining Path, Dr. Wang did research on cooperative collision warning system based on V2X technologies, big data analysis on vehicle driving patterns, simulation assessment of advanced vehicle technologies, crash data analysis, and road safety evaluation. Dr. Wang received her PhD degree in transportation engineering from Tongji University in China. She also worked as an intern at BMW Technology Office for a half year and a postdoctoral researcher at Path for a year and a half. Okay, Ping, you can go ahead.
Okay, thank you for the introduction. Today, my talk is learning from demonstrations based on adversarial inverse reinforced learning. Its application is for the decision-making task in the lane change scenario. This research has gone through 3 phases. First, we learn a simple decision-making strategy based on the adversarial inverse reinforced learning. In the second phase, we learn the multiple decision-making behaviors based on the information maximization and AL. In the third phase, we learn an adaptable decision-making policy and its reward function based on machine learning and adversarial inverse reinforced learning. In my later talk, I will call it AL. So let's see what we did in the first phase. Here are some backgrounds for the imitation learning and reinforced learning and the inverse reinforced learning. I think most of you are familiar with these advantages and disadvantages, so I won't talk about it here. Here are some other new methods. One is the generative adversarial imitation learning. It can learn a policy by involving a discriminator, but this method, through this method, you can get the reward function. Another method is called the adversarial inverse reinforced learning. It also uses a discriminator, but we can learn both the policy and the reward function. Our study is built upon this adversarial inverse reinforced learning. Here is our AL framework. So to train the discriminator, we fed the expert data and the general data to it, and the discriminator learns to distinguish whether the data is from the expert or from the generator. So this is the expression of the discriminator. After many updates of the discriminator, we can get its weights, and we use the discriminator to construct the reward function here with this expression. And we also add a semantic reward term. We call it augmented AL. And with this reward function, we will train the generator with the trust region policy optimization method to update the parameter of the generator. And with the new generator, we will generate new data and then feed the newly generated data and the expert data to the discriminator. This loop will go over and over again until it gets converged. We apply this method to the decision-making task. That is, we want to learn the decisions on when and where to make the lane change maneuver at the next time step. So here is an illustration. So for the yellow car, which is the eco vehicle, it tries to decide how to make the lane change. So for our action space, we designed as discrete. We consider the 2 directions from the longitudinal direction and the lateral direction. So in the longitudinal direction, the yellow car can decide which gap it wants to merge into whether gap 0, gap 1, gap 2, or gap 3, which is staying on its current lane. On the lateral direction, it decides whether to make the lateral movement right now. So in total, there should be 8 actions. Because we are doing the decision-making tasks, so it's better to design the action as discrete. And following this, we can add another planning module or control module to get the continuous control variables. Here is our testing results. We compare several methods, the L plus the sparse reward. This is our method, and we also implement other methods. Here is the results. The black dotted line is the expert data. The red line is our results. We can see, compare with the other methods, our methods is very close to the expert data for these 4 evaluation metrics. So for the total reward, this evaluation matrix is the accumulated reward in 1 episode. So each dot is from 1 episode. And we have like 15,000 episodes. And the successful ratio is the successful episode over all the episodes that we did in the experiment. We can see the red curve almost reached to 1, which means very high successful rate. The decision steps is the decision-making time steps in 1 episode. So that means if the vehicle decides to make a lane change, so the module will accumulate the time step that it uses. The changing steps is the lane changing steps, which means the time step that the vehicle actually making the lateral movement. So these 2 curves should be stable at the end, because if the agent learns how to make the decisions, it should have a stable driving behavior. And from our results, you can see the red curve and the black dot line is very close, which means our agent actually learns how to make the lane change. Here is a simplified simulation version to illustrate what I just said. Let's see. Oh, it seems it's so strange. Okay, and hold there. Oh.
There's no play option, right?
Yeah, but I think it worked before. Yeah, but I can't quit.
You just press exit on your keyboard.
Yeah, I tried, but
It's frozen?
Yeah, it doesn't work. Oh, so it doesn't work even though.
Yeah, alternatively, we can play the next presentation and then you can go back to yours after that.
Yeah, I will see.
Or you can do that right now. You can
Let me try it again. Oh, it doesn't work. Oh, it works. Can you see it now? Can you see my screen?
Not yet.
Oh, here, not yet. Oh.
Yeah, coming through.
Yeah,
Yes.
can you see it?
Yes, you can try to play that in this.
Yeah, I will play it in this mode.
Yeah.
Okay. Oh, it seems it doesn't work.
It's not loading.
Yeah. Okay, maybe I need to create an. Do I still have time, or you need to let the next speaker go first and then
You,
I come?
you have time. You have time. The next speaker will be pre-recorded video, so that's fine. It's not wait.
Okay. Yeah, maybe it's better to go with like a slides. Maybe later back we can come back to see whether the video works. Okay.
Certainly.
Yeah. So here I will talk about the second phase, which is learn the multiple decision-making strategies based on the information maximization and the AO method. So from the AO method, that I just talked about, we just learned an average policy. That means even though there might be multiple driving styles in the collected demos, but we can only learn an average policy. So that may be not what we wanted in some situation, because we want to learn the multiple driving styles if they are exist in the driving demos. And there are some research which can learn the different driving styles from the demonstrations, but they have their limitations. From the InfoGil, you can only learn the policy. And there is another method, it's the InfoL. We call it InfoL because we integrated the information maximization and the AO method. And we use this method to learn the multiple driving styles in an unsupervised way. I will talk about this in a little bit detail. So let's first see like how the InfoGil works to give you a demonstration. So first, if we have the expert demos like this from the basic behavior cloning and the GIL methods, we can learn a policy. The policy just generate average trajectories or average circles. You can distinguish from the different colors. And from the InfoGil, it can learn different colors. So this method just applied to very simple toy examples or computer games. We want to apply our proposed method, the InfoGil, to more practical and complicated applications like our lane change scenario. So we did some modification here. This is our objective function. We designed the discriminator with this function. And we also have the loss function for the discriminator. Here I didn't go into details, but generally the discriminator wants to distinguish the expert data and the generate data. The generator wants to generate data that is very similar to the expert data. So it can fool the discriminator. Here is the framework. We have the discriminator, the generator, and that I talked in the AO framework. And here we have another posterior. This is another network. We feed the generate data to it and we update it and guess its weights. And with the discriminator, we build up the reward function. And after we get the reward function, we can tune the generator, and the generator will generate new data. So here we involve the posterior. Actually, it tries to learn a latent variable C, which can be considered as the multiple styles. Here are some details. Here is the simplified network structure. We feed state action to get the value, and we use the value F to get the value of the discriminator. And for the posterior, we feed the state action to get the category or to get the latent variable C. And based on this latent variable, we also feed the states to get the final action. Then we can get the generator. It can generate new trajectories. And here are our results. We compare several methods. Our method is the InfoL, and the we compare with the InfoGil method, the AO, GIL, and expert data. So here we can see, like in the expert data, there are 3 driving styles. From our method, we can generate very similar distributions with the expert data. but with the other methods, we can get very close distribution with the expert data. Even though the InfoGIL can also have distinguishable distributions, but it's different from the expert data. And we also compare the distribution of some evaluation metrics, like the maximum acceleration, maximum speed in different driving styles. The green one is the expert data, the yellow one is our method, and the purple one is the InfoGIL results. We can see our method, the yellow box match the green box well compared with the purple one. That's another way to show the effectiveness of our method. Here is the third phase. We learn an adaptable decision-making policy based on the method learning and the AO method. So here is a little introduction about the method learning. It means learning to learn. It learns the components in the learning procedure, like learning the hyperparameters, learning the network optimization or the network architecture. In our study, we use the optimization-based method learning methods. This also includes many specific methods, like the MAMO, first order MAMO reptile. In our study, we use the reptile for the update of the meta learning framework. I will talk about it later. Let's see how the meta AO works. So for the meta learning, usually there are two training phases, the meta training and meta testing. From the meta training, we have different driving tasks, and from these tasks, we can get a model. We call it F theta. And then across different driving tasks, we can update the model parameter theta. And this process includes a learner and a meta learner to update the parameters. And after we get the parameter theta from the meta training phase, we can go to the meta testing phase. In this phase, we will have new driving tasks which are not included in the meta training. And these tasks is usually have limited data, and we want to use the limited samples to adapt to get the result, the parameters for this task very quickly. So in this step, we will try to adapt the data to let it work with the new tasks. So here is the details about how it works. First, we have the driving task, for example, the driving task 1, and we feed it into the network, we call it F theta, and then we can get the loss to the gradient. And after we get the updated weights, we can use the testing trajectories to get the new loss with the new parameters for this driving task. And for the other driving tasks, we can also get the loss with the newly updated parameters. So here in this step, we can sum the new loss over different driving tasks, and then we can do the gradient descent. And the newly updated parameter will be broadcasted to different tasks, and the task will go up again. And this loop will iterate over and over. So here are like more details, how we prepare the driving data and how we build the network. The network actually includes the discriminator network and the generator network. And here is the loss function, how we train the discriminator and how we train the generator, how we construct the reward function. And for the model data, it includes the parameters from the discriminator and the parameters from generator. And we can do the update for these two networks and get the newly updated parameter theta prime. So for the meta learner, actually it should have these three phases as I just talked about. We get the loss from the new parameters and then sum the loss over different tasks, and then do the gradient descent to get the data. but here actually it involves the second order derivative. So it's very high compute. There is very high computation cost. So generally we will try to avoid it. So we use the reptile to do it, because in our tasks, we have two networks in the structure, and we will update it with different update iterations. So it's not easy for us to use the second derivative. That's why we use the reptile methods. With the reptile, we can update the discriminator and the generator with different iterations. And we can get the state updated very simply. So we will use this equation to do the update, and then we can get the new parameters for the meta testing task. So here is the algorithm. For the outer loop, we have like 2,500 iterations. For the inner loop, we do 2 iterations, but inside the inner loop, they have different iterations, updated iterations for the discriminator and generator. You can see we use 50 for the discriminator, there's 1 for the generator, and this will help us get the good results more easily. Here is our experiments. So in the collected driving data set, maybe like different drivers will have different driving behaviors. For example, there is aggressive driving behavior, or conservative driving behavior, or neutral driving behavior. In our tasks, we will take the aggressive and conservative driving behavior as the meta training tasks, and use the neutral one as the meta testing tasks. And we suppose there are only like 5 or 10 or 50 driving trajectories in the meta testing tasks. So we can see whether with this limited number of expert trajectories, we can get the good driving models. Here is our learning results. We have 4 categories of the evaluation metrics. First, the discriminator performance. Under this one, we also have 2 sub-metrics, which we call it the discriminator performance and the generator performance. Here is the discriminator performance. So generally, the discriminator will try to output 0.1 for the expert data, because if it's expert data, it will have a high probability. But if it's the generator data, it should output 0, means that the discriminator knows like the data is from the generator. But when it trained with the generator, both of these values should go to 0.5. And our results show that perfectly match the analysis. At first, it goes up, try to be as high as possible, for example, as 1 as possible. And for the generator performance, it's try to go to 0. But after training for a while, it goes to 0.5 here, goes to 0.5 here. So that means we train the discriminator well. And here is the performance for the generator. We use the total reward. As we know, the policy or the generator should have a high reward in the end. So we can see the reward goes up. So this also match our analysis. And the third evaluation matrix is the absolute performance. We have 3 sub-metrics: the running step, decision step, and successful ratio. The run step is the decision step that is the duration of an episode before a termination, which means like before a crash, or before if the episode is too long, it will also terminate. That means like how long your episode can go. The decision step is the decision-making process in an episode. The success ratio is the successful episode over all the episodes. We can see like these curves goes to stable and very distinguishable. So that means the agent learns the decision-making behavior, and eventually it can make the decision-making very stable. And for the successful ratio, it's close to 1, and we can see the training agent can make very high successful learn change behavior. And for the fourth evaluation matrix is the driving kinematics. We access the maximum acceleration, minimum acceleration, and maximum speed. Here we can see these distinguishable styles. That means the agent can learn different driving styles, and they are quite distinguishable. That means that also another proof that our agent can actually adapt to the new tasks with the training parameters from the meta training tasks. And that's the meta training results. We also have the meta testing results. As I mentioned, I use one meta training tasks with limited number of expert trajectories. And we compare two methods. Our method is the meta-AL. Another baseline method is the AL, which is pre-trained with all the training tasks and then fine-tuned on the meta testing task. And we compare the training loss, which should be goes down. As we can see, the red curve is our results. The blue curve is the baseline method. Our curve, you can see the loss stay very low. And for the total rewards, you can see our results. The total reward goes up very quickly, but the baseline methods stay very low. And for the successful ratio, our method goes to a very high successful ratio very quickly, but the baseline methods, it's very slow. Also, we have the driving performance for the maximum acceleration, minimum acceleration, and the maximum speed. Here is the distribution. So here, the red curve is the expert distribution. The blue curve is our results. The green curve is the baseline method. So we can see for all of these four evaluation metrics, our methods, the red curve, the blue curve match the expert curve very well compared with the green curve. That's also another proof to say our methods is very close to the expert driving performance. Okay, here, that's my presentation. Thank you.
Thank you, Pin. Very informative. If you can quickly go back to the slides where you categorize those different drivers.
Different drivers here?
Yeah, 22. The one in the middle, he seems more aggressive than the one on the left, right? He's honking and ready to fight at the same time. The picture.
Sorry, you mean the left is the aggressive one. This is more conservative because he pays much more attention to the driving environment.
He seems aggressive to me.
Yeah, but this is just a picture to illustrate what I want to say.
For the sake of time, maybe we'll not go to the detailed question. One detailed question you can find in the chat box. Joe Chow raised a question regarding the reward function. Maybe you can answer him in the chat directly. That's easier.
Okay.
Thank you once again, Pin. Let's go to the last presentation.
Thank you for having me.
So our last presenter, last but not the least, is Dr. Yang, Dr. Hao Yang. Let me load up his video first. And it's quite hard. So share screen 3, I guess. So Dr. Yang is an assistant professor focusing in transportation engineering in the Department of Civil Engineering at McMaster University in Canada. He completed his master and PhD degree at the University of California, Irvine. He was also awarded a second master degree in statistics from UC Irvine as well. He completed his bachelor at the University of Science and Technology of China. Dr. Yang's research focuses on the design and evaluation of connected and automated vehicles to improve vehicle mobility and energy efficiency for the rapid development of smart cities. And as the first or the second presentation, Seihan mentioned, this work is also related to his work, so kind of echo to what Seihan has presented. Yeah, let's watch the video right here. And if you have any question for Dr. Yang, just please feel free to type in the chat box.
Everyone, thank you very much for joining my presentation today. It's actually my great pleasure to present at ITSC this year. First of all, I want to make a brief introduction about myself. My name is Hao Yang, and I'm currently an assistant professor in the Department of Civil Engineering at McMaster University in Canada. My major research interest is about the development of various applications of connected autonomous vehicles in mobility and driving safety. In the presentation today, I will introduce one of my recent research in the anomaly behavior management. This research will develop an individual vehicle control system to reduce the impact of the anomalous drivers with the help of the connected vehicles. Here is the outline of the presentation. First, I will go through the research background, including the problem statement and the potential challenges, and then introduce an anomaly behavior modeling method. After that, I will show how to develop the proposed anomaly management system and evaluate the system with microscopic simulations. Finally, I will give the conclusions of the study and some future recommendations. Traffic safety is one of the most important issues in transport system. Vehicle collisions on the road will result in a lot of deaths, injuries, and property damages. For example, in the United States, every year there are more than 6.7 million vehicle crashes, and they will cause 2.7 million injuries and 36,000 fatalities. In addition, the U.S. National Highway Traffic Safety Administration reported that vehicle collisions are the leading cause of the deaths for young populations under age 34. Moreover, we find that vehicle collisions are also one major cause of the road congestion. Usually, you will observe a very long queue ahead of the vehicle collisions, and this will significantly reduce the quality of the transport services. Among all the vehicle collisions, almost 30% of them are caused by anomalous drivers who were performing distracted driving, impaired driving with the use of alcohol or drugs, aggressive driving, and so on. It becomes very urgent for us to propose innovative technologies or some policies to mitigate the impact of the anomalous drivers on the road and improve the driving safety. Currently, a lot of innovative solutions have been proposed to handle the issue caused by vehicle collisions on roads. The most popular one is a vehicle collision avoidance system, which consists of two parts. The first part is the collision detection, which will be applied to identify the potential collisions of one vehicle to their leaders and their surrounding vehicles. And then based on the identified collision, the system will provide warning messages to drivers or apply autonomous control actions directly to avoid vehicle collisions. There are also some other systems such as adaptive cruise control and automatic emergency braking system. Both of them have the functions to prevent vehicle collisions on roads. However, the drawback of the existing study is also very clear. First, most of the existing study does not have any accurate model to describe the anomalous driving behaviors with human errors. Without this model, the prediction about the potential collisions is not accurate, which will reduce the efficiency of the control strategies. Second, there isn't any systematic anomaly behavior management system for large-scale road network, especially for the management of a huge number of the vehicles on the road. The research in this presentation is trying to solve these two challenges. In this research, we will use connected vehicles for the development of anomaly behavior management system. Actually, it's well known that connected vehicles are ones with the capability of communication with other ones and the roadside infrastructures. These vehicles will be equipped with certain communication devices. In the future, we can also anticipate that they will be equipped with various sensing technologies such as camera, radar, LiDAR, and so on, and some partial automation features. These technologies are actually very perfect for us to develop the proposed system. In this research, we also made some assumptions about connected vehicles so that the implementation of connected vehicles will be reasonable in the near future. First of all, we see that connected vehicles can monitor their own and the surrounding vehicle behaviors and share the information with each other. This is actually the basic functions of connected vehicles. And second, we say only the connected vehicles can receive control actions and prevent collisions with anomaly drivers, so that we will only provide the management for connected vehicles and try to use these connected vehicles to improve the performance of the entire traffic. With that, I can summarize the objectives of this research. First of all, we will model anomaly driving behaviors and reproduce human errors so that the impact of the anomaly drivers can be accurately evaluated. Second, we will develop a multi-layer hierarchical management system to reduce the impact of the anomaly drivers in large-scale road networks, especially the network with a huge number of vehicles. In this research, the first task is modeling anomaly behaviors. To do that, we have to understand the human errors in car following behavior. The first one is a perception limit, which would be the sensing limit of human drivers to speed changes. Usually, human drivers are not very sensitive to small speed changes, especially when they are far away to their leading vehicles. For a regular human driver, they are not sensitive to the speed difference less than 5 to 20%. The second type of error is the middle of road. This one is related to the driving tasks of human drivers. Usually, a human driver will perform two driving tasks. The first one is the primary driving task, which will be speed control, car following, and lane changing. And the second one is called a secondary driving task, such as calling phones, conversation, eating, and so on. If the driver is performing both of them, then the mental load applied to the human driver will increase dramatically. In that sense, the human driver cannot handle the primary driving task accurately. This will result in more deviated speed and acceleration. If the human driver is fully engaged in some secondary tasks, such as dialing phones and reading maps, and they do not perform any primary driving task, then they actually take their eye off the road, which will be the third error. In this case, the eye off will significantly increase the response time delay for the human driver to various traffic conditions. In this research, we applied an arable car following model which was developed by Huang and Peng in 2010. The model is a stochastic car following model. It assumes that acceleration is a function of spacing, speed difference, and response time delay. In the paper, a linear regression model is applied to describe the relationship. The model can easily integrate the errors that we described in the previous page. For the first error, perception limit is actually applied to determine the speed difference. The equation here shows how we use the perception limit to estimate the speed difference. Usually for normal drivers, PR is selected as 0.1. For anomaly driver, the value could be 0.1 or even larger. Actually, in a larger PL indicates a driver is not sensitive to speed change, so that they cannot control the speed well with respect to the leader. For minor of error, it actually determines the estimated acceleration applied for the vehicle. Actually, the estimated acceleration follows an extreme value distribution. That means the acceleration estimated from the stochastic model, and the standard deviation is the function of spacing. If the vehicle is performing mind-off, then the difference between the estimated acceleration and the acceleration from the stochastic model should be at least one standard deviation. If it is a normal driving, then it's smaller than one standard deviation. Also, we need to identify the durations for the vehicle to perform in normal driving and the mind-off driving. Actually, both durations follows a log normal distribution. The two figures here shows the distributions for these two durations. For the eye of error, usually it's modeled with the response time delay. Actually, the response time delay is applied for normal driving too. For normal driving, the delay is small, and the duration of normal driving follows an exponential distribution. For eye-off driving, the time delay is very large, and the duration should follow a uniform distribution. So that's all about the arable car following model that we use to model the anomaly behaviors. Then we can work on the development of anomaly behavior management system. First of all, we will introduce a hierarchical architecture to handle the large-scale issue. In this architecture, we will divide the city-level road network into 4 layers. At the bottom is the in-car level, which will try to handle individual vehicles. Above that is the section level. It will try to manage vehicles in a single road segment on the intersection. And on top of that is a region. It represents a small area with multiple segments and intersections. On top is the city. It will manage a city-level road network. For each layer, there is one manager, which are trying to control traffic and vehicles in their corresponding area. In this study, we are particularly interested in the potential collisions, which are modeled by the arable car following model. We want to control the connected vehicle behaviors, such as the speed control for the nearby vehicle and detour instructions for the connected vehicles far away. Now we will go through the management system applied for each level. First, the city manager implements a lane group level navigation system. This system can provide a dynamic vehicle routing with the estimation of the turning cost at each junction, and it will also predict the travel time delay with respect to the potential collisions on each link. The region manager will deploy lane level routing strategy. This strategy can provide the lane level paths for connected vehicles to avoid the potential collisions on the road. The optimal lane is actually selected based on the updated lane cost and the potential collision information on each lane. Finally, at the section level, an anomaly driver avoidance system will be applied to assist the connected vehicles. The anomaly driver avoidance system actually has 2 steps. The first step is data collection, where we will use connected vehicles to monitor the dynamics of the connected vehicle and its leader, including the location speed and acceleration rate. Then in the second step, we will use this dynamics information to detect the errors that the leader is performing. If the leader is performing mind-off driving, we will introduce speed control, where we will restrict the acceleration rate of the connected vehicles so that we can maintain a larger gap to the leader. And in that sense, we can prevent the potential collisions of the connected vehicle to the leading vehicle. If the leader is performing eye-off, depending on the level of the risk of the connected vehicle to the leader, we will apply different strategies. If the risk is low, we will apply the same speed control action to the mind-off. If the risk is pretty high, means that the connected vehicle cannot avoid the potential collision by the speed control, then we will instruct the connected vehicle to make lane changes so that it can try to detour the anomaly leader. Now we can evaluate the benefit of the proposed anomaly behavior management system. We will start with evaluating the anomaly driver avoidance system with a synthetic example. The 2 figures here actually shows the trajectories from the experiment. The black, green, and red lines represent the leading vehicle trajectory, which is chosen from the NGSIM dataset, the anomaly follower, and a regular third vehicle. In the figure on the left, the anomaly vehicle does not apply any errors, while on the right, the mind-off and eye-off errors are all applied. We can see that at the end of the simulation, there is one vehicle collision occurs at the anomaly vehicle, and it will also cause the high risk of the collisions for the following regular vehicles. We can explore more details about the collision based on the spacing profile and the error profiles. First, from the spacing profile, we can see that the spacing of the anomaly driver is reduced to 0, which indicates that there is a collision for the anomaly driver. From the error profiles, we see that during the collision, the anomaly driver actually experiences severe IOF errors. At the same time, the anomaly driver is performing acceleration, while the leading vehicle is conducting deceleration. In that sense, the anomaly vehicle cannot respond to the leader's deceleration. This will result in the collision that we observed at the end of the simulation. The figure here shows the safety improvement of the vehicle following the anomaly driver after applying the anomaly driver avoidance system. Here we use the time to collision to measure the safety. With a higher value of time to collision, the risk of the collision will be smaller. Then from the figure we can see that with the control, the time to collision for the vehicle following the anomaly driver can all be larger than 2.5 seconds, which will be sufficient for the vehicle to avoid collision. Also, after control, the distribution of TTC is much more concentrated compared than the base case. This means that the behaviors of the vehicle after control will be more consistent, which means they will have safer trip on the road. Besides the synthetic experiment, we also evaluate the proposed management system with a microscopic simulation in a large-scale road network. In the experiment, a real city-level network, Interstate Highway 66 in Arlington, Virginia, is chosen. The figure here shows the geometry of the network. In the experiment, realistic traffic data from the network is chosen, and we simulate more than 30,000 vehicles. The realistic assumption about the connected vehicles that we specified previously is also applied. And we also introduced the arable coupling model to describe the behaviors of 128 vehicles, which are assigned as anomaly drivers in this simulation. And they are assigned randomly to all the OD pairs. In addition, the hierarchical architecture about the anomaly behavior management system is also deployed. We activate the management system for all levels, city, region, and section. The table here summarizes the safety and mobility benefit of the proposed system for connected vehicles and regular vehicles in the simulation. Here we set the penetration rate of connected vehicles as 20%. First of all, connected vehicles, we can see that the number of the crashes for each vehicle is reduced by up to 7%, and for the average travel time delay is reduced around 43%. Similarly, we can observe the reductions about the crashes and the travel time delay for regular vehicles, but the benefit is a little bit smaller than connected vehicles. With that, we summarize that the proposed management system has significant benefit on improving the performance of both connected and non-connected vehicles, and the savings of connected vehicles is higher than regular vehicles. We also conduct a sensitivity analysis of market penetration rate of connected vehicles. The figure on the left shows the savings in vehicle crashes under different MPR of connected vehicles. The figure on the right shows the savings in travel time delay. By observing these two figures, we can see that there exists a concave relationship between the market penetration rate of connected vehicles and the savings in vehicle crashes and travel time delay. In general, the optimal MPR is observed around 30%. At the optimal value, the vehicle crashes can be reduced around 11% for connected vehicles and 48% in travel time delay. The sensitivity analysis of traffic demand levels is also conducted. The figure here shows the savings in travel time delay and the vehicle crashes and the different demand levels. Similarly, a concave relationship between the benefit and the demand levels can be observed, and we found that the optimal demand level can be achieved around 1.1 to 1.2 with respect to the base demand level that we defined for the simulation. And at the optimal demand level, the travel time delay can be saved up to 54%. For the vehicle crashes, it's reduced by up to 19%. So that's all about the major contents of this research. In the summary here, we incorporate an variable coupling model to describe anomalous driving behaviors and user information to develop a knowledge management system. Also, we propose a hierarchical anomaly behavior management system to improve driving safety and mobility in a large-scale road network. And we also conduct a sensitivity analysis of NPR or connected vehicles and demand levels. We can see that there will be a lot of things that we can do to improve this study. First, we see that the proposed system has some weakness on handling high NPRs of connected vehicles. And I plan to introduce a centralized control system to overcome the high NPR issue. Second, we see that for connected vehicles, the vehicular communication is a critical issue. It's better to integrate the system with a realistic vehicular communication model so that we can understand the real benefits of the proposed system. Finally, in this study, we only consider individual vehicle control without the help of the roadside infrastructure management. It would be better to integrate both of them so that we can gain global optimization. So that's all about my presentation. Thank you very much for your attention. I'm really sorry that I cannot join you online today. Here's my email address. Please feel free to send me email if you have any questions. And I'm really happy to have more discussion with you in the future. Again, thank you very much. Please enjoy the rest of the workshop.
Thank you. Thank you everyone for still staying here. And as Hao mentioned, enjoy the rest of the workshop, and the rest of the workshop is just the closing speech. So Chris, Guodong, Guoyuan, Yihan, do you want to add some words on this workshop?
I just want to thank you, Ziren, for organizing it. You did a great job, and thank you to all the speakers. Very interesting presentations today.
Yeah, really thanks your work for organizing this fantastic workshop. So there are lots of talks about simulation, simulators. Hope everyone we can think offline to find more interesting usage of the simulators.
Thank you. Guoyuan and Yihan, do you have any words, or it's fine?
No, not really. I fully agree with this. Is a very interesting workshop. I have myself also learned a lot from all speakers.
Yeah, me too. Well, I think it's really a great workshop, and thank you all the contribution, and thank you for all the audience. It's really great. I learned a lot also.
Yeah, as I observed, we reached maximum of 63 people in our channel, which is very good because I attended some of the workshop yesterday, 8 people, 10 people. It's really hard for all of us to get together right now. So really great. So for those who want to stay and have some casual chat, Chris and I will, stay in here. After everyone's leaving, and we can leave, but we will stay in here for those ones who want to hang out. And thank you all again, especially for those ones who are in at already midnight right now. Thanks for staying, and we will be sending out an email to everyone maybe in future 2 or 3 weeks. Thank you, everyone.
Thank you.
Thank you.
Bye.
Bye. And Zhan, maybe one question. Do you know if all the recorded workshop or presentation will be available later on?
It will be definitely available to all the attendees who registered. And I think it will be available to us eventually. That's why I meant I will send an email in 2 or 3 weeks, because maybe not necessarily in the next week.
Okay.
Eventually it will be available.
Okay, got it. Thank you.
Yeah, that would be great, right? To more
Right.
more access to that.
Yeah, excellent information.
Mm-hmm. Just curious for Chris and Yihan, you guys are in EDT. Have you already taken your lunch yet, or You guys are hungry right now.
I've already eaten my lunch.
Yeah, me
had-
too.
Great. I just took mine during the last presentation.
Yeah, I ate during the presentation.
Just to interrupt you guys, and thank you guys for organizing this really interesting workshop. Really nice. I've learned so much. And my name's James Yang from Texas Tech, and I'm a professor in mechanical engineering department. So my research focus on human modeling, simulation, and biomechanics. But recently, we're really interested in driver behavior modeling, actually. So trying to learn something. So of course, Chris, I'm sure I met you before in NETS, right? So I used to work I was a Korean student before.
Oh, okay. Okay. Yeah, we're doing some driver modeling work as well. Working with John Lee up at Wisconsin.
Yeah. So that's really I'm trying. Just want to say hello to you.
Yeah. Hi. So where are you located now?
I'm in Lubbock, Texas.
Lubbock.
Texas.
Okay. Okay.
Yeah. So you attend the ITS conference every year?
I don't usually. No.
All right.
Are you attending the rest of the conference this week?
No. This is the first time I just started because I saw in LinkedIn this advertisement. Looks really interesting. So this is my first time actually just listening to this workshop.
Yep. Yeah, me too, I think.
Just curious, James, where did you see that from LinkedIn? Which connection? Is that Chris or?
So, Ziran, what they're asking for?
No, I mean, which connection did you see that post from LinkedIn?
Oh, on LinkedIn. On LinkedIn, I saw the post actually. That's what I sent the email and got a reply.
Yeah, it's very good that we can advertise our thing on LinkedIn, because so many people, they don't even know there's a workshop at the very last minute. So it's great, yeah.
And the opportunity is so easy to attend. We don't have to travel to Greece.
That's true.
If
one advantage.
We could. That'd be better, right? It's beautiful there, it looks like, right?
Yeah.
But I mean, if we can meet in person, that would be more memorable. I mean, we can hang out together, have dinner, maybe right now, right? Have a dinner together.
Yeah, that would be fun. We'll get back to that. There's a couple years until the next one, right?
Yeah, I would think so. Well, I mean, not necessarily in some of the places. I know in China, they already have some offline kind of thing, meetings in person. For the US, definitely maybe not next year. I was registering for ACE World Congress, and this says it's going to be held in hybrid format. There will be virtual, there will be in person in April, which I highly doubt whether that's safe or not.
No, I don't think so. I don't think so. Until maybe next year. Until right now, I'm not sure we'll be kind of completely be normal. I kind of suspect.
Yeah.
I'm thinking later next year it might happen because we might have a vaccine by then. But early next year, I'm not too confident. So Ziran, are you attending the rest of the conference this week, or is just the workshop?
Actually, not. Yeah, just the workshop. That's it. I don't have any paper for ITSC, but I do have 3 papers for IV, which is next month, October 30th. And we also, Gloria and I will also host another workshop on IV as well.
Wow,
Intelligent Vehicle Symposium. Yeah.
Great.
And that was already postponed to October. That was originally in June in Vegas, where we already plan, things to do in Vegas, and then this thing kicks in, and we don't have any option.
Yeah. Wow.
We were waiting for a long time for those conferences to go back to the United States since 2018, the Maui one, ITSC in Hawaii, and
Yeah.
then we don't have anything in the States for ITSC or IV. And this year we were so excited about IV is going back to Vegas, and then this whole thing happened.
I know. I was really fortunate to have a good travel year in 2019. I went to 5 new countries for
Really?
for business that I hadn't been to before. So it was a big year. And China was one of them. I was in China last October, around October.
Cool.
So,
which city? Do you remember still?
Shanghai.
Okay. Okay.
So you attend the Chinese SAE conference?
No, it was a small sort of workshop at what's the university there?
Tongji University?
Yeah, Tongji.
Oh, okay. That's I think that's like a German conference to host with Tongji together, right?
Yeah,
that's October 20 something. Yes, I think I also attend. I didn't see you.
I think this was a different event, even smaller. It was
really?
very small event. There were a few simulation folks there.
Oh, okay.
Yeah, it was neat to have the opportunity to visit.
That's your first time to China?
Yeah, it was my first time in China.
Oh, okay.
Yeah.
So
very interesting.
So what do you see? What do you saw and what you heard before you head in there? What's the difference?
Well, one of my colleagues from NADS had been to China before during his MBA. It was for the MBA program. They visited China, so I had seen some really interesting videos and pictures that he took of traffic. So I didn't know what to expect for the traffic. I think I was expecting some, really chaotic and lots of.
That's in India. That's in India.
Yeah. Well, he showed us some video in China too, but I don't know if it was a different town, small town maybe.
No traffic lights, right? That's no traffic.
It was organized. It was all organized in Shanghai. Yeah. In fact, there were some really cool intersections downtown in Shanghai that were where the street was illuminated, like there were lights embedded in the street, and they would illuminate to help people cross or not cross. There were some really interesting intersection designs. And we went to the top of Shanghai Tower.
Oh, that's cool.
Couldn't see too far because of the pollution, but it was still a great view.
October time, right? October, yeah, might not be the best.
So you said last year went to 5 countries. Well, which other 4 countries?
Well, I went to ESV in the Netherlands. That was in that was in Eindhoven. So that was one, and then we made our way by train. First I was at a workshop in Paris. What was that? Was that IV? Was IV in Paris a couple years ago?
Yes, that's IV.
Yeah, so I did a workshop with Fujita Gunaratne of Toyota in Paris, and then we went over to Eindhoven where I did the ESV, and then we headed back by train over to London, and then I went up to Leeds, to University of Leeds, and saw their simulator, gave a presentation to their group, and then And just kind of in between, you know, we had lunch in Belgium, so I count that because we stopped to have lunch.
Okay, all right,
Yeah.
that's all Europe. That's good.
If I had just driven through it, I wouldn't count it, but we were there for like an hour. So yeah, it was really, really great. Look forward to traveling again.
Me too. So Chris, have you been to any place this year before March or April?
No, no. In fact,
not at all.
I could have gone to. I mean, TRB happened early in the year in January. I usually go to TRB, but I didn't go this January because I was so busy with a couple projects. I didn't. So I skipped TRB, and it turned out that was probably my only chance to travel in 2020.
Definitely the only thing. That's the only thing.
It's fine.
All right. I'm gonna check out, guys. Nice meeting you guys up here. Okay, really learned a lot. Really good. Dr. Wang, really good organizer. Really nice.
Thank you. Thank you.
See you guys. Hopefully later on. All right. Okay. Bye.
Bye.
Take care.
Let's see the others. Ping, are you still there? And Yan?
Yeah, I'm here. Listen to your talk. You are talking. Yeah. Oh, thank you for your reminder. Yeah, I just you know, before your call, I just checked the email and mark it to my own note. Yeah, tomorrow I will give a presentation.
I'm good. We made it, so that's fine.
Yeah. So you said this all of these talks will be recorded and will be available maybe in about a few weeks.
I think so. Maybe you can see from your screen, it's still recording, and it was not initiated by me. It was initiated by the host of this workshop, and he transferred the host to me. So I don't even know which folder this recording will be going to, but there definitely will be a recording.
Okay. Yeah.
Probably directly go to the host of ITSC, and then they will distribute that to all of the others. I will ask. I will check with them.
Okay. That's good.
Good talk, and sorry you had trouble with your video.
Yes. Actually, I this slide I used the video before it works. I don't know like why it doesn't work this time. But
yeah, I didn't know why that
much.
It's so frustrating.
Yeah, I hope my presentation, like the audience can understand most of my presentation. I'm not sure whether I'm explaining it very clearly or very like I think maybe I speak a little bit fast. I'm not sure whether the audience.
No, that's very good to me. It's very informative. The only reason that we don't understand maybe it's too high tech, too hardcore for us. You did a lot of work, and so for those who, including me, are not really in the field of machine learning, we don't really understand, but we appreciate what you have done.
Okay, thanks. Yeah, at least you know like what kind of topic I did.
Yeah, really nice presentation, and also I think that technique that you are using is really state of the art, and I would say like a lot of industry are also exploring that, and we didn't really put that into the production yet, but I think that's a really great technique to explore. And I think one huge challenge there is actually getting a really realistic simulated environment to kind of like test that kind of like algorithm or even train rows parameters. One of the key challenges to make it work into production.
Yes, you are correct. So yeah, well, one of the reasons that why we use simulation is, you know, we just a research group, so we don't have so many like PhD students or postdocs to help us process the like a perception module, like process the images or sensor data. So that's why we choose to start with the simulation first. once we have some good results in simulation, we will try to integrate more real world sensors like the camera or the GPS data or other kind of data. First, also try into the simulation first, and then maybe step by step, try to see whether part of the work can be integrated into the industrial level. We actually want to see part of the work can be used in practice. And I also hear some people from industry, they are very interested in this kind of topic and want to see how they can use it in their own production or in their own research. So yeah, you're right. It's a very tough task to really apply the whole thing into practice.
Yeah, maybe integrate that into a kind of hybrid planner is one way. To put that into one module could be one way, but I guess like the latency could be another challenge. Yeah, while I listened to those this kind of like presentations, one question came to my mind is that, so while we are using this kind of like simulator or the behavior model to do the connected automotive vehicles development, do we actually think about, for example, like to apply those research outputs to the other application? One thing is that, for example, in the current ride sharing or even the car insurance industry, we kind of like can monitor some of the behaviors of the drivers and can also maybe to detect some anomaly or using some driver model to identify which is a dangerous driver. So do we, like a research committee actually working on that application as well, or it's just maybe a naive idea?
Oh, yeah, I can maybe answer some of your questions. So actually, in our group, we have another research project which is trying to detect whether the scene is anomaly or whether this scene is at high risks. Yeah, you mentioned whether the driver is like a very risky driver or yeah, the situation is risky. But like a very related work in our group is we will detect whether the scene is at high risk. Like for example, you know, like Tesla, the car has like some accidents in different states, and actually for those scenarios, the detection model works well. It can detect all that is a truck, but actually when combining with other data, like the truck is actually still and it's it stay on the lane, it's not moving. If you combine this kind of information, actually you know this thing is at high risks. So we are trying to do that kind of work, try to know whether the scene is dangerous, even though your detection model works. So this is the related work that we are doing right now.
Cool. Thank you for sharing that. Professor Chris, like you also mentioned that you are also working on the driver behavior model. Could you also share some insights about, like, for example, what could be the potential applications for driver models? Definitely it's useful in simulation. How about the other applications?
Yeah. I think for, I think one of the main motivations is that in designing automated vehicles that people will use and accept and be comfortable in and enjoy, you have to take into consideration how drivers respond in the situations that AVs are going to respond in. So if it's a critical situation or a situation where an AV needs to make a decision, respond to surrounding things, then if that vehicle understands how drivers respond in those same situations, then they can respond very naturally. And I think that's one of the big motivations for considering that as a type of simulation or a type of modeling that fits in with modeling everything else, the sensors, the the vehicle, the path planning. I think if you don't understand how drivers respond and you're not able to capture that in some sort of a model that you can then sample from, then people may not be comfortable with your automated vehicle. So
Yeah,
I think that's kind
exactly.
of right.
Yeah, and yeah, totally agree. And the other things that I'm thinking is like for example, in industry, we all, for example, as a planning engineer, I need to deploy some algorithm and then test that in the simulation. And we normally kind of give the scores based on different evaluators.
Yeah.
But you know, like setting different threshold for different evaluator is not trivial because like there are so many different scenarios. So I was also thinking that like some of the driver model can actually integrate into the evaluator so that when we evaluate, we can use a human concept to see, oh, whether this is a good behavior at this kind of scenarios.
Yeah, that's interesting. I always wonder, like earlier we had a presentation today about abnormal, you know, the abnormal detection, and I always think about in that case whether you should really be understanding and learning what normal behavior looks like or what abnormal behavior looks like. I feel like there's infinite ways to be abnormal.
Yeah, exactly.
In different ways, but there's a range of accepted behaviors that you would call normal. So in some ways, it might be easier to understand normal and then detect deviations from that. But I don't know. People are so different, you know?
Yeah.
Yeah, exactly.
So different from one another.
Yeah. Thank you so much.
Davey, I see you are still online. Do you forget to log off or? Because some of the people, they might forget to log off. There was another one who just logged off. I asked him, why do you stay so late? He was like, I just left in the middle, and when I come back, there's only 8 people.
You might be gone already. I see that Jiren Wang is down there.
No, that's another. I log into 2 of my devices. And the last one, if you check that, ZWizN, that's my wife's mobile phone. I just want to check the quality of our meeting.
So,
So
almost a third of the people are you.
Yeah, we contribute 3 headcounts. So yeah, if that's it, we only 3 people, so we can close it. So yeah, you are still in the valley, right? In Silicon Valley, right?
I'm on Mountain View.
Oh, cool.
Yeah.
Cool. Yeah,
maybe
we can
very
catch
close
up.
to you. Yeah.
Yeah, catch up later.
Yeah, for sure. Yeah, I will go back to eat some lunch. Then.
Okay.
Yeah. Bye bye,
So,
everyone. Nice
all
to
right,
meet
bye.
you guys.
Thank you, Chris.
Yeah.
Thank you.
Yeah,
Talk
thank
to
you
you
so
guys.
much. Have a nice one. Bye bye. Yeah.
Bye.